Imagine astronomers on July 1st, 2025, scanning the night sky as they do every night, searching for anything unusual, anything out of place in the familiar patterns of our solar system. And then, there it is, a fuzzy spot of light that shouldn't be there, moving in a way nothing should move, too fast, wrong direction, not following the gravitational rules that govern everything bound to our sun. And then the calculations come back with something extraordinary. This isn't from our solar system at all. It's a visitor from interstellar space, a comet from another star system passing through ours. They named it 3I Atlas, the third confirmed interstellar object we've ever observed. It passed us safely, never came close to Earth, gave us an incredible opportunity to study something ancient and alien, a wanderer from beyond carrying chemistry from another star, offering us a glimpse of distant stellar systems we'll never visit. But tonight we're going to ask a different question. What if it hadn't missed us? Hello, and welcome to the Sleepy Astronomer. If this is your first time drifting through the cosmos with me, welcome. I'm so glad you're here. And if you've travelled with me before through these quiet explorations of space, it's wonderful to have you back for what might be one of our most thought-provoking journeys yet. Whether you're settling into bed, curled up somewhere comfortable, or perhaps gazing up at that same sky where 3I Atlas passed safely by, I'm so grateful you're here to explore this question with me. If you enjoy these peaceful explorations of the cosmos, I'd be so grateful if you'd subscribe to join us for more cosmic journeys. And if this question intrigues you, a gentle like helps others discover these late-night wanderings through space. Now, before we go any further, let me offer you this profound comfort. 3I Atlas did not hit Earth. It passed through our solar system exactly as predicted, gave us invaluable scientific data, and continued on its billion-year journey through the galaxy. You're safe. We're safe. The disaster we're about to imagine didn't happen. What we're exploring tonight is a thought experiment, a way to understand both the remarkable nature of interstellar visitors and the incredible fortune of their trajectories. When something is moving at 60 kilometers per second, 216,000 kilometers per hour, coming from beyond our solar system, carrying the momentum of eons, well, the difference between a safe passage and a collision is just a matter of degrees, a slight variation in angle, a tiny change in trajectory. We got lucky. Wonderfully, spectacularly lucky. But here's what makes this question so fascinating. It's not just about disaster, it's about understanding. When you imagine what would happen if an interstellar comet struck Earth, you begin to appreciate the vastness of space, the emptiness that protects us. You start to understand the physics of impacts, the energy contained in velocity, the difference between something from our solar neighbourhood and something from beyond. And perhaps most remarkably, you realise how much we've learned just from observing objects that pass safely by. Oumuamua in 2017, that strange, tumbling visitor that sparked so many questions. Borisov in 2019, our first confirmed interstellar comet. And now 3I Atlas in 2025. Larger, brighter, better studied than either of its predecessors. Each one a messenger from the cosmic deep. Each one teaching us about star systems we'll never reach. Tonight, we'll explore what 3I Atlas actually is and where it came from. We'll imagine what would have happened if its trajectory had been just slightly different, if Earth had been in its path. We'll walk through two scenarios, one where a relatively small nucleus strikes us, and another where the larger estimates prove true. We'll see what makes interstellar impacts different from asteroids born in our own solar system. We'll visit the history of impacts on Earth and our current efforts at planetary defence. And perhaps most importantly, we'll learn to appreciate the gift of the near miss. The fact that a 3-eye atlas came, showed us wonders, and departed without incident. That we live in a time when we can detect these visitors, study them, learn from them, and watch them pass safely by. So settle in, take a deep breath, and let yourself relax into this journey. The question is sobering. What if 3-eye atlas hit Earth? The answer? Well, the answer teaches us about cosmic velocities, planetary resilience, and the remarkable fortune of empty space. But first, we need to meet our visitor from beyond. So let's begin at the beginning, on that July night, when astronomers first spotted something unusual. The Atlas Telescope System, short for Asteroid Terrestrial Impact Last Alert System, which is perhaps the most reassuringly responsible acronym in astronomy, scans the sky every night from its observatory in Chile. It's designed to find near-Earth asteroids, those rocky remnants from the early solar system that occasionally wander too close to our planet. The telescopes take images, computers compare them to previous nights, and algorithms flag anything that's moved or appeared where it shouldn't be. On July 1st, 2025, the system flagged something. At first glance, it looked like a comet. There was a fuzzy appearance, that characteristic blur that comes from gas and dust surrounding an icy nucleus. Nothing too unusual about that. We discover comets regularly. But then the astronomers started calculating its trajectory, and that's when things became extraordinary. The orbit was wrong, not slightly wrong, not we need to refine our measurements wrong. Fundamentally, impossibly wrong for anything that belongs to our solar system. You see, everything born around our sun, every planet, asteroid, comet, and speck of dust, is gravitationally bound to it. Objects can have elliptical orbits, taking them far out and bringing them back in. They can have nearly circular orbits like Earth's, but they're all following paths determined by the sun's gravity, moving at speeds that make sense for their distance. This object was moving at 60 kilometers per second. To give you a sense of scale, Earth orbits the sun at about 30 kilometers per second, and we're moving quite briskly, thank you very much, completing our annual journey in exactly 1 year as you'd expect. The fastest comets in our solar system, those coming from the distant Oort cloud, falling inward from the outer dark, might reach 40 or so kilometers per second as they approach the sun. 60 kilometers per second is, well, it's excessive. Wonderfully, impossibly excessive. And the shape of the orbit sealed it. Not elliptical, hyperbolic, which in orbital mechanics terms means not coming back. This object was passing through our solar system on its way to somewhere else. It wasn't bound to our sun. It was just visiting. Within hours, the confirmation came. We were looking at an interstellar object, something from beyond, a wanderer from the space between stars. They gave it the designation 3-eye atlas. The 3-eye means it's the third confirmed interstellar object we've ever detected. The atlas comes from the telescope system that discovered it. Simple, elegant, and carrying that slight thrill that comes from knowing you're looking at something that formed around another star. Now, here's where things get delightfully uncertain, in that way that makes astronomy both fascinating and occasionally frustrating. We're not entirely sure how big 3-eye atlas is. The estimates range from about 440 meters across to a rather more substantial 5.6 kilometers. That's quite a range, isn't it? The difference between a large building and a small mountain, and you might wonder how we can be so uncertain about something we're observing with some of the most sophisticated telescopes humanity has ever built. The problem is that We can't actually see the nucleus directly. What we're seeing is the coma, that cloud of gas and dust surrounding the icy core, glowing and fluorescing as sunlight warms it and solar radiation excites its molecules. It's like trying to determine the size of a light bulb by measuring the glow around it. You can make educated guesses based on brightness and activity level, but there's uncertainty built into the process. What we can say with confidence is that 3I Atlas is active, beautifully, dramatically active. As it approached the Sun, it developed an impressive tail, that classic comet feature, streaming behind it as solar wind pushes gas and dust away from the nucleus. It brightened significantly, making it easier to study, which astronomers around the world very much appreciated. And here's something wonderful. It's reddish. That might not sound particularly exciting at first, but the colour tells us something profound. That reddish hue comes from organic compounds, complex carbon-based molecules that have been altered by billions of years of exposure to cosmic radiation. These organics formed in the disk of gas and dust around another star, perhaps 7 to 14 billion years ago. Think about that for a moment. This object is older than our solar system. It was already ancient, already wandering before our sun even ignited. The chemistry in 3I Atlas, those organic compounds giving it that reddish tint, that's alien chemistry. Not alien in the science fiction sense, but in the most literal way possible. It's chemistry from another stellar system. Different ratios of elements, different formation conditions carrying the signature of wherever it was born. So where exactly did it come from? We don't know, and we probably never will, not with certainty. Based on its trajectory, we can trace its path backward through the galaxy, but that only tells us what direction it came from, not which star it originated around. It's been travelling for billions of years. Stars move, galaxies rotate. The precise stellar neighbourhood where 3I Atlas formed has long since dispersed and rearranged itself. What we can imagine, though, is its story. Picture a planetary system forming around a young star billions of years ago. Planets coalesce from the disk of dust and gas. Some grow large. Their gravity is powerful, disruptive. Small, icy bodies, comets and planetesimals, get flung around by these gravitational giants. Most settle into stable orbits. Some crash into planets or get consumed by the star. But some get ejected entirely, flung outward with enough velocity to escape the star's gravity. And then they wander. For billions of years, these orphaned comets drift through interstellar space. The galaxy is vast, mostly empty, unimaginably dark and cold. Occasionally, one of these wanderers happens to pass near another star system, and very occasionally, remarkably rarely we're watching when it does. Oumuamua in 2017 was the first, that strange, elongated object that tumbled through our solar system, accelerated slightly in ways we're still debating, and departed before we could study it properly. It sparked so much speculation, some of it quite creative, about what it might be. Then came Borisov in 2019. Definitively a comet, clearly from interstellar space, and while smaller and less spectacular than 3I/Atlas, it gave us our first good look at a comet from another star system. It was oddly comforting, actually. Looked and behaved much like our own comets. Suggested that comet formation is similar wherever it happens. And now we have 3I Atlas. Larger, more active, better studied than either of its predecessors, because we detected it earlier and because our observational capabilities keep improving. Hubble observed it. James Webb turned its infrared instruments toward it. Ground-based telescopes around the world tracked its progress. For a brief window of time, a few months in the cosmic calendar, 3I Atlas was the most studied object in the solar system that wasn't technically from our solar system. What we learned is that interstellar comets are not particularly rare. The statistics based on our 3 detections so far suggest that roughly 1 interstellar object passes through the inner solar system every year. Most are too small or too faint for us to notice. We're only seeing the largest ones. As our detection systems improve, as we build better telescopes and more sophisticated scanning programs, we'll find more. The galaxy, it turns out, is full of wanderers. Billions upon billions of orphaned comets and asteroids, drifting in the dark between stars. We're swimming in interstellar debris, though the distances are so vast that actually hitting one is extraordinarily unlikely. 3I Atlas gave us a show, brightened beautifully as it approached the sun, developed that impressive tail. Let us study its composition, its behaviour, its ancient chemistry. And then, as predicted, it began to fade, moving outward, away from the sun, back toward the interstellar dark from which it came. Eventually it became too faint to observe. Our telescopes lost track of it. It's still out there, of course, still travelling at 60 kilometres per second, but now it's beyond our ability to see. In a few thousand years, it will leave our solar system entirely, and then it will wander for billions more years through the vast emptiness, until perhaps, by chance, it encounters another star system. And if that system has astronomers, maybe they'll spot it too, give it their own designation, marvel at this ancient visitor, wonder where it came from. But that's the real 3I Atlas, the one that passed safely through our solar system, taught us extraordinary things and departed without incident. Tonight, we're imagining something different. We're imagining what would have happened if 3I Atlas had been on a collision course with Earth. If that July detection had come with the terrifying realization that this interstellar visitor wasn't going to miss us, that we had months to study it, to calculate, to understand exactly what was coming, but not enough time to stop it. Let's imagine that slight variation, that subtle difference in trajectory. What if 3I Atlas had Earth in its path? When we talk about astronomical paths, we're dealing with angles and velocities that seem almost impossibly precise. A comet travelling at 60 kilometres per second across the vast distances of space, its path determined by billions of years of gravitational interactions, by every star it's passed near, by the cumulative effects of forces so small they seem negligible, but add up over cosmic timescales. Change that trajectory by just a few degrees, and you change everything. Instead of passing safely through the inner solar system, 3I Atlas's path intersects with Earth's orbit at exactly the moment Earth happens to be there, which, given the tiny size of Earth compared to its orbital path, picture a marble on a track that's 100 million miles around, would be remarkably unlucky. But that's what we're imagining tonight. Remarkable catastrophic bad luck. The detection happens the same way. July 1st, 2025. Atlas telescope system flags an unusual object. Calculations begin. And then, the realization. This isn't just an interstellar visitor passing through. This one is going to hit us. We'd have months of warning. Maybe 4, maybe 6, depending on when exactly the collision was calculated to occur. That's simultaneously too much time, and not nearly enough. Too much time to contemplate what's coming, to watch the news cycle spiral, to see the calculations refine day after day, each refinement narrowing the uncertainty, but confirming the terrible truth. Not nearly enough time to do anything meaningful to prevent it. And here's the difficult truth we'd face. We probably couldn't stop it. Our current planetary defense capabilities, which are actually quite impressive and have improved dramatically in recent years, are designed for objects that belong to our solar system. Asteroids we've been tracking for years, sometimes decades, objects with known orbits that we can predict far in advance, calculate precisely, watch carefully. If we see one heading our way with enough warning, we have time to launch a mission, time to send a spacecraft on an intercept trajectory, time to nudge it, even slightly, which over months or years translates into missing Earth by a comfortable, safe distance. The DART mission in 2022 proved this concept beautifully. We deliberately crashed a spacecraft into an asteroid called Dimorphos and measurably changed its orbit. Not by much, just a few minutes in its orbital period. But enough. Enough to demonstrate that if we had years of warning, if we had time to prepare and launch and intercept, we could defend ourselves. It was a triumph of planetary defense, a demonstration that we're not helpless, that we can protect our world. But DART took months to reach its target, months of careful navigation, of approach, of preparation, and that target was moving at normal solar system speeds, following a predictable orbit, going nowhere particularly quickly. 3. I/Atlas is moving at 60 kilometers per second. It's not bound to the Sun, so it's not following a predictable elliptical orbit we've been tracking. By the time we detect it, it's already here, already committed to its trajectory through our solar system. It's not slowing down, not being captured, not giving us years to prepare. Launching an interceptor mission would be like trying to catch a bullet with another bullet, except both bullets are travelling at speeds that make actual bullets look stationary. Could we even launch something fast enough to catch it? Possibly. Our fastest spacecraft have reached impressive velocities. New Horizons, on its way to Pluto, achieve speeds of about 16 kilometers per second. The Parker Solar Probe, using the Sun's gravity to accelerate, has reached speeds over 190 kilometers per second at perihelion, though that's with the assist of the Sun's gravity well. But launching something, navigating it to an intercept, arriving with enough time and precision to make a difference, all within a few months? The engineering challenges would be immense, perhaps insurmountable. Nuclear deflection, the dramatic last resort often portrayed in movies, usually accompanied by Bruce Willis or similarly determined individuals, might seem like an option. The concept is straightforward enough. Detonate a powerful nuclear weapon near the incoming object, vaporize part of its surface, and the expanding vapor creates thrust that pushes the object off course. In theory, this works. We've run the calculations. We've done the simulations. In practice, with months of warning and an object moving this fast through a hyperbolic trajectory, the amount of deflection you'd achieve would be minimal, probably not enough to matter. You might change its course by a few kilometers, but Earth is over 12,000 kilometers across. You'd need to deflect it by thousands of kilometers to ensure a miss, and the physics simply doesn't give you that much push from a single detonation. Multiple detonations? Possibly, if we had multiple nuclear-capable spacecraft ready to launch, which we don't. If we had time to launch them sequentially or simultaneously, which we probably wouldn't. If we could navigate them precisely enough, which would be challenging. So in our scenario, we'd know it was coming. The realization would spread through the astronomical community first. Emergency meetings, urgent communications, double-checking calculations because surely there must be an error, but the math would keep coming back the same. Then the wider world would learn. Governments briefed, emergency protocols activated, plans developed for evacuations, for preparations, for whatever mitigation might be possible. Every telescope on Earth and in orbit would be watching 3i Atlas, gathering data, trying to understand exactly what we're dealing with. Scientists would calculate and recalculate, measure the brightness, study the spectral signature, analyze the tail development, try to determine the size of the nucleus hidden within that glowing coma, refine impact predictions, where it will hit, when exactly what angle. And gradually, the awful certainty would settle in. 3. I-Atlas is going to hit Earth and there's nothing we can do to stop it. We can prepare, we can evacuate threatened regions, we can try to preserve knowledge, stockpile supplies, plan for survival, but we cannot prevent the impact itself. Now this is where that size uncertainty becomes absolutely critical. Remember, we're not sure if 3I Atlas is 440 meters across or 5.6 kilometers across. That range of uncertainty exists because we can't see through the coma to the nucleus itself. We're making educated guesses based on how bright it appears, how actively it's outgassing, comparing it to other comets we've studied. But comets are variable. Some are more reflective than others. Some are more active for their size. The brightness doesn't translate directly to size with perfect accuracy. And unfortunately, this difference isn't just a matter of academic interest. It's not a footnote in a scientific paper. It's the difference between a terrible regional catastrophe and a potential extinction event. The difference between millions of deaths and billions. Between civilization damaged and civilization ended. Let's put this in perspective because the human mind doesn't naturally grasp these scales. The Tunguska event in 1908, when an asteroid or comet fragment exploded in the atmosphere over Siberia, involved an object about 50 to 60 meters across. It flattened 2,000 square kilometers of forest. 80 million trees knocked down in a radial pattern, radiating outward from the explosion point. The blast was equivalent to roughly 10 to 15 megatons of TNT. Had it struck a populated area, a city, a densely inhabited region, the death toll would have been catastrophic. Hundreds of thousands, perhaps millions, depending on the location. But it was perhaps 50 times smaller than even the conservative estimate of 3I Atlas's size, 50 times smaller in diameter. And volume, mass, scales with the cube of diameter. So 3I Atlas at its smallest estimate would have roughly 125,000 times more mass than the Tunguska object. Of course, it's not just about mass, it's about energy, and energy is 1/2 mass times velocity squared. That velocity term, squared, is what makes high-speed impact so devastating. At the large end of the estimates, 5.6 kilometers, we're talking about an object comparable in size to the Chicxulub impactor. That's the asteroid or possible comet that struck the Yucatan Peninsula 66 million years ago and rather famously ended the reign of the dinosaurs, along with about 75% of all species on Earth at the time. Chicxulub was somewhere between 10 and 15 kilometers across, so 3I Atlas at its largest estimate would be smaller, perhaps half the diameter, but not that much smaller, really. Enough to be in the same category of civilization-ending catastrophe. And remember, it's moving faster than Chicxulub was, much faster. Chicxulub probably struck at around 20 kilometers per second, which is already terrifyingly fast. 3I Atlas would be hitting at 60 kilometers per second, 3 times the velocity, 9 times the kinetic energy per unit of mass. Energy in impacts scales with the square of velocity. This is one of those physics relationships that starts out seeming reasonable and quickly becomes terrifying when you actually plug in the numbers and think about what they mean. Most asteroids that threaten Earth are moving at roughly 15 to 25 kilometers per second when they hit. Those speeds are largely determined by Earth's orbital velocity plus or minus the asteroid's approach angle and velocity. Earth is moving at about 30 kilometers per second around the Sun, so a head-on collision with an object in a similar orbit adds those velocities together, while a catch-up collision from behind would subtract them. Even comets from the Oort cloud, those distant, icy visitors from the outer reaches of our solar system, falling inward from distances of thousands of astronomical units, typically hit at around 40 kilometers per second at most, and usually less. 60 kilometers per second is in a different category entirely. That's 216,000 kilometers per hour, if you prefer to think about it that way. Though I'm not sure that helps with comprehension. It's fast enough to cross the entire United States in about 20 seconds. Fast enough to go from the Earth to the Moon in under 2 hours. It's absurdly fast. Blessedly, impossibly fast. The kind of speed that makes you deeply grateful for the vast emptiness of space that makes such collisions extraordinarily rare. And here's another factor that matters. 3I Atlas is a comet, not an asteroid. You might think that distinction doesn't matter much when something is about to hit your planet at cosmic velocities, and you'd be partly right. The impact is going to be catastrophic either way. At these speeds, composition almost becomes irrelevant, because everything behaves like a fluid on impact. Everything vaporizes, everything turns to plasma. But the composition does affect exactly how that catastrophe unfolds, particularly in the atmospheric effects that follow. Comets are icy. They're sometimes called dirty snowballs, though that's a bit misleading and doesn't really capture their nature. They're actually more like icy dirt balls. Silicate rock and organic dust held together by frozen water, carbon dioxide, methane, ammonia, and various other volatiles. This makes them less dense than solid, rocky asteroids, less mass packed into the same volume. You might think that's good news, relatively speaking. Less mass means less impact energy, right? Yes, but only partially. The lower density does reduce the total impact energy somewhat, but the velocity more than compensates. And when a comet strikes at these speeds, all that ice vaporizes instantly, completely, catastrophically. The water doesn't splash. It doesn't have time to behave like liquid water to flow or spread. It goes straight from solid to plasma in a fraction of a second, skipping the liquid phase entirely in a process called flash vaporization. And that vaporized water adds its own effects to the impact. More atmospheric interaction, more steam injected into the stratosphere, more debris lofted higher, different chemical reactions in the aftermath, all that hydrogen and oxygen interacting with vaporized rock, with atmospheric nitrogen, creating different compounds. Rocky asteroids are, in some ways, cleaner, more straightforward. They hit, they vaporize, they excavate an enormous crater, they throw up immense quantities of pulverized rock and molten material. Terrible, destructive, catastrophic, but predictable. We understand rocky impacts quite well. Comets are messier. The vaporized ice adds complexity to the atmospheric effects, creates different patterns of global cooling because water vapor and ice crystals behave differently than rock dust in the stratosphere, injects different chemicals into the upper atmosphere. None of this makes the impact better, to be clear, just different in its specific mechanisms of catastrophe. But we're getting ahead of ourselves. Before we can talk about aftermath, about what happens in the hours and days and years following impact, we need to establish another critical variable. Where does it hit? Earth is 71% ocean. If 3I Atlas were to strike randomly, purely by chance, the most likely scenario, by far, is an ocean impact. Specifically, given that the Pacific Ocean alone covers about 165 million square kilometers, roughly a third of Earth's total surface, probably somewhere in that vast expanse of water. A land impact is certainly possible, would be different in its effects, more immediately catastrophic for anyone nearby, but potentially less globally devastating in some specific ways. No massive tsunamis, for instance, which we'll discuss shortly, but more direct destruction of whatever happens to be at the impact site. A polar impact adds its own complications, striking the ice sheets of Antarctica or Greenland, vaporizing billions of tons of ice instantly, melting even more, creating different sea level and oceanic circulation effects. But for our exploration tonight, we're going to focus primarily on the most likely scenario, an ocean impact. Specifically, a Pacific Ocean impact, because that's both the most probable statistically and, in many ways, the most dramatic in its consequences. The Pacific is deep, vast, and surrounded by heavily populated coastlines. An impact there would affect more of humanity more dramatically than almost any other location. Now, before we walk through what actually happens moment by moment, we need to acknowledge what we've been building toward. That size uncertainty creates two very different futures. The small impact, and it pains me slightly to call something 440 meters across small, but in the context of planetary catastrophes and extinction-level events, it is relatively small, would be a regional disaster, devastating, horrific, world-changing, killing potentially millions of people, disrupting global civilization, economies, supply chains, causing immense suffering, but survivable. Humanity would endure. Civilization would be damaged, but would eventually recover. The large impact, 5.6 kilometers, would be something else entirely. This would be a mass extinction event, not necessarily the complete extinction of humanity. We're adaptable, and some would surely survive, but certainly the end of our current civilization, the end of our current way of life, the death of most large animals on the planet, in the oceans and on land, an event on the scale of what killed the dinosaurs, reshaped the planet's ecosystems, and reset the evolutionary clock. So we're going to explore both, walk through each scenario carefully, understand what we're dealing with at each scale. Because they're both worth understanding, both teach us something crucial about impacts, about planetary resilience, about the delicate balance that allows complex life to thrive. And because the truth is, until an object like this is very close, until those final days or hours when we can make extremely precise measurements, we wouldn't know with certainty which scenario we're facing. Those months of warning would include agonizing uncertainty about exactly how bad it's going to be. Imagine that. Knowing something is going to hit, knowing it will be terrible, but not knowing if you're looking at a catastrophe you might survive, might recover from, might rebuild after, or an apocalypse that will end everything familiar, everything built, everything you've known. The observations would continue right up until impact, telescopes gathering data continuously, scientists refining estimates, the size of the nucleus gradually becoming clearer as 3I/Atlas approaches the inner solar system, as we get better angles, as we can measure it with more precision. The uncertainty narrowing day by day, week by week, until finally, perhaps just days before impact, we'd know, really know, whether we're facing a regional devastation or global extinction. And then there would be nothing left to do but wait, prepare as best we can, and hope we'd made the right decisions, evacuated the right people, preserved what could be preserved. But let's not stay in that uncertainty. Let's walk through both possibilities. Let's understand exactly what we're imagining in both cases. Because understanding the physics, understanding the consequences, helps us appreciate both the danger and the remarkable fortune that usually protects us. We'll start with a smaller impact, 440 meters. Still catastrophic, still terrible by any human measure, but survivable. Something humanity could eventually recover from. And then we'll face the larger possibility, the extinction-level event, the 5.6-kilometre scenario that would change everything, that would divide human history into before and after, that would be comparable to the worst mass extinctions in Earth's geological record. Both are worth understanding. Both teach us about the physics of impacts, about the resilience and fragility of our planet, about the incredible fortune that allows us to exist at all. So take a breath, stay with me. We're going to walk through some difficult scenarios, some sobering possibilities. But remember, this didn't happen. 3i Atlas passed safely by, gave us wonder and knowledge, not destruction. These are thought experiments, ways of understanding our universe, our vulnerability, and our remarkable fortune. So let's begin with the first scenario that's catastrophic but survivable. A 440-metre comet nucleus, roughly the size of a large office building laid on its side, or if you prefer a more dramatic comparison, about 4 times the height of the Statue of Liberty, striking the Pacific Ocean at 60 kilometres per second. The impact location matters enormously, so let's be specific. Imagine it strikes in the central Pacific, roughly midway between Hawaii and the coast of Japan. Deep water, perhaps 4 or 5 kilometres deep. Far from land, but not so far that the consequences won't reach every coastline surrounding this vast ocean. The final moments before impact would be extraordinary, in the most literal sense. 3i Atlas would be visible from across the Pacific as it approached, a bright point of light getting rapidly brighter, growing from a dot to a streak across the sky. Those near the impact point would see it as a brilliant fireball, brighter than the sun, trailing plasma and superheated air. And then it hits. At 60 kilometers per second, the comet doesn't splash into the water the way you might imagine. It doesn't penetrate smoothly, pushing water aside. At this speed, water might as well be concrete. Actually, water might as well be solid rock. The comet encounters so much resistance, so much compression that everything, the comet, the water, the air, behaves like it's in an explosion. Which, to be fair, it is. The comet vaporizes on contact. Completely. Every atom of ice, every grain of rock and dust. Converted to plasma in a fraction of a second. The water directly in front of it vaporizes too. And the water beyond that, and the seafloor beneath. The impact punches through 4,000 meters of water and excavates a crater in the bedrock below, all in the span of perhaps 2 or 3 seconds. The energy release is approximately 10,000 megatons. To put that in perspective, and perspective is challenging with numbers this large, the largest nuclear weapon ever tested, the Soviet Tsar bomber in 1961, yielded about 50 megatons. This impact would be 200 times more powerful than that. 200 of the largest nuclear weapons ever created, detonating simultaneously in the same spot. Think about that for a moment. The Tsar bomber test in 1961 was visible from 1,000 kilometers away. The mushroom cloud rose to a height of 64 kilometers, well into the stratosphere. The atmospheric pressure wave circled the Earth 3 times before dissipating. Windows shattered hundreds of kilometers from the test site, and that was 50 megatons. This would be 200 times that. A fireball forms, several kilometers across, reaching temperatures of tens of thousands of degrees, perhaps 100,000 degrees at the core, hotter than the surface of the sun, not by a little, but by a factor of 10 or more. The thermal radiation alone, just the light from this explosion, the electromagnetic radiation across the spectrum, would be fatal to anyone with direct line of sight from hundreds of kilometers away. If you were standing on a ship 300 kilometers from the impact point, the flash would arrive in 1 second, the speed of light. For that instant, before you could even process what you were seeing, before your brain could interpret the signal from your optic nerve, the thermal radiation would be intense enough to ignite clothing, to cause immediate severe burns. Then, about 15 minutes later, the blast wave would arrive, and by then the distinction would be somewhat academic. The flash would be visible from satellites, obviously. From the International Space Station, astronauts would see a brilliant point of light suddenly appear on Earth's surface, brightening rapidly, briefly outshining entire continents in their field of view, then fading over several seconds as the initial fireball cooled and expanded. They'd have questions. They'd have a great many questions. Whether satellites would see it. Military early warning systems, designed to detect missile launches and nuclear detonations, would certainly see it, and might have some very tense moments before sensors confirmed this wasn't a nuclear exchange but something arguably worse. The pressure wave radiates outward through the water at supersonic speeds. Not a normal wave, this is a shock wave, a discontinuity in the medium, travelling faster than sound in water, which is already quite fast at about 1,500 meters per second, carrying pressures that crush and destroy. Submarines hundreds of kilometers away would be destroyed instantly if they were at depth. Their hulls would crumple like aluminum cans. The crew wouldn't even have time to understand what happened. But the surface is where the most dramatic and far-reaching effects begin. The water directly above the impact point, thousands of cubic kilometers of it, is displaced. Upward, outward, the ocean surface bulges, then explodes outward as a wave. Actually calling it a wave doesn't quite capture it. It's more like a moving mountain of water, hundreds of meters high at the point of origin, spreading outward in all directions at the speed of a jet aircraft. This is a tsunami, but not like the tsunamis we're familiar with from earthquakes. Earthquake tsunamis are usually caused by sudden vertical displacement of the seafloor. A section of ocean floor drops or rises during a quake, and the water above it follows, creating waves that propagate outward. Those waves are often barely noticeable in deep water, perhaps a meter or two high, but they carry enormous energy and grow dramatically when they reach shallow water near coastlines. An impact tsunami is different, more energetic, more violent, starting with that initial explosion of water, that massive displacement at the surface, creating waves that are already enormous in deep water. From the impact point, the wave spreads outward at roughly 700 to 800 kilometers per hour in the deep ocean, slower than the shock wave through the water itself, but faster than any ship could flee, faster than most aircraft could evacuate at low altitude. The wave height decreases as it spreads, energy distributed over an ever-expanding circumference, following the physics of wave propagation, but it remains formidable. By the time it's travelled 1,000 kilometers from the impact, it might be 20 or 30 meters high in deep water, still a wall of water that would obliterate anything in its path. Let's follow this wave to its inevitable destinations. Hawaii would be hit first. The islands are roughly 3,000 kilometers from our hypothetical impact point. The wave would arrive in about 4 hours, maybe less depending on the exact location and trajectory, on the underwater topography it crosses. 4 hours. That's enough time for warning. Seismic sensors would detect the impact instantly. It would register on every seismograph on the planet as a massive, sudden event off the scale of anything in the historical data. The Pacific Tsunami Warning Center, located in Hawaii itself, would immediately issue alerts, emergency broadcasts, evacuation orders, every available channel carrying the same message, Move to high ground immediately. 4 hours to evacuate islands, to get everyone to high ground, to move inland, upward, away from the coasts. It's not enough time, really. Not for everyone. Not for the elderly, the sick, those without transportation. Not for tourists who don't know the islands, don't know where to go, don't know which roads lead to safety. Not for the inevitable chaos, the traffic jams, the panic. Not for people who doubt the warnings, who want to watch, who don't understand the scale of what's coming. When the wave arrives, it would be perhaps 15 to 25 meters high, maybe more depending on the bathymetry, the underwater topography that can focus and amplify tsunami waves as they encounter shallow water. It would wash over coastal areas, over beaches and resorts and harbours, over everything within a few kilometres of shore depending on elevation. The death toll would be in the thousands, possibly tens of thousands, despite the warning time. The destruction would be total along the coasts, everything near sea level simply gone, scoured away, reduced to debris scattered inland. But most people would survive. The islands have high ground, have mountains, have protocols, though probably not for something of this magnitude. It would be catastrophic, devastating, the worst disaster in the island's history. But most of the population would make it to safety if they acted quickly. Then the wave continues west, toward Japan and the Philippines, toward the entire western Pacific Rim. Japan would have perhaps 6 to 7 hours of warning, enough time for more organized evacuations. Japan has excellent tsunami preparedness. They've experienced these disasters before, understand the danger intimately, have systems in place, have building codes designed for this, have practiced evacuation routes and procedures. But this wave would overwhelm their preparations. It would be larger than anything in their historical record, larger than the devastating 2011 Tohoku tsunami, which was itself catastrophic, which killed nearly 20,000 people, despite Japan's advanced warning systems. Tokyo Bay, Osaka, every coastal city, the wave would penetrate deep inland, especially in low-lying areas. The death toll would be immense. Hundreds of thousands, possibly millions, depending on how effective the evacuations were, depending on how many people could reach high ground in time. The economic damage would be incalculable. Japan's infrastructure, so much of which is necessarily coastal for a nation of islands, would be devastated, ports destroyed, industrial areas flooded, power plants, refineries, manufacturing centres, gone. The Philippines, Indonesia, Southeast Asia, all would be struck. Islands would be particularly vulnerable. Low-lying atolls might be completely overtopped, everything washed away, entire communities erased. Coastal cities would be destroyed. The death toll across the region would be horrific, magnified by population density, by poverty, by lack of infrastructure for rapid evacuation. And the wave continues, crossing the Pacific toward the Americas. The western coast of the United States would be hit perhaps 10 to 12 hours after impact. California, Oregon, Washington. Longer warning time than Hawaii or Japan, more opportunity for evacuation, but also more coastline to evacuate, more population to move. San Francisco Bay, Los Angeles, San Diego, Seattle, every major coastal city. The wave would funnel up bays and harbours, amplifying as it encountered shallower water and constricted channels. Some areas might see waves 30 or 40 metres high, 10 stories, higher than most buildings near the coast. The evacuation would be the largest in American history. Millions of people told to move inland immediately. Highways would be jammed. Some would make it. Many wouldn't. Not from lack of trying, not from ignoring warnings, but from the sheer logistical impossibility of moving, that many people that quickly over infrastructure, not designed for simultaneous mass exodus. South America's Pacific coast would face similar devastation. Chile, Peru, Ecuador, countries that have experienced tsunamis before, countries with their own warning systems and protocols, but nothing of this magnitude. Coastal cities destroyed, fishing fleets obliterated, death tolls in the hundreds of thousands. New Zealand and Australia's eastern coast would not be spared. The wave would arrive after circumnavigating various Pacific islands and submarine features. Perhaps less organised, less focused, but still dangerous, still deadly, still capable of destroying coastal communities. And here's something that might not be immediately obvious. The wave doesn't stop after hitting land once. It reflects, bounces back, crosses the Pacific again, though smaller, less organised. There would be secondary waves, tertiary waves, the ocean sloshing back and forth, like water in a disturbed bathtub, though on a planetary scale. These subsequent waves would be smaller, but would still be dangerous for days afterward. Coast Guard stations would broadcast warnings, do not return to coastal areas. The danger is not over. The total death toll from the tsunami alone would likely be in the millions, perhaps 5 million, perhaps 10 million, depending on how effective evacuations were, on how much warning time people had, on luck and preparation and 100 other factors. But as devastating as that is, as impossible as it is to truly grasp the human cost of millions of deaths, we need to remember this is the smaller scenario. This is survivable. Most of humanity lives far from the Pacific coast. Most of the world would not be directly affected by the tsunami at all. People in Africa, Europe, inland Asia, the interior of the Americas, they'd watch the catastrophe unfold on television, horrified but physically safe. The economic disruption, however, would be global and profound. The Pacific Rim includes some of the world's largest economies: Japan, China's eastern coast, the western United States, South Korea, Taiwan. The destruction of port facilities alone would disrupt global trade for years. Container ships couldn't dock, supply chains would collapse. Everything connected to Pacific trade routes, which is a substantial portion of global commerce, would be affected. Silicon Valley, largely coastal California. If we lost the tech industry's physical infrastructure, if we lost the people, the expertise concentrated in those regions, the companies, the data centers, the technological setback would be immense. Financial markets would crash, not just from the immediate destruction, but from uncertainty, from fear, from the massive reallocation of resources that would be necessary for recovery. Stock markets would close, currency exchanges would become chaotic, the global financial system would face its greatest test. Insurance companies would collapse. The claims would be beyond anything they're prepared for, beyond anything imaginable in their actuarial models. Governments would have to step in. National debts would soar. The economic recovery would take decades. Food supplies would be disrupted. Much of the world's rice is grown in coastal Asia. Fishing industries would be devastated. Boats destroyed. Coastal fishing communities gone. Marine ecosystems disrupted by the churning and sedimentation. Agricultural land near coasts would be contaminated by salt water, rendered useless for years. But, and this is crucial, civilization would continue. Most infrastructure outside the coastal zones would be fine. Most farmland would be unaffected. Most people would be unaffected directly. It would be a catastrophe, certainly. The worst disaster in human history by far, but not an extinction event, not civilization ending. Then there are the atmospheric effects to consider. 10,000 megatons is a lot of energy. but it's released in one place at the surface. Much of it goes into the water, into excavating that crater in the ocean floor, into creating the tsunami and shock waves. Some goes into the atmosphere as a massive plume of vaporized water, vaporized rock from the seafloor, and debris. This material would be lofted into the stratosphere. Millions of tons of fine particles, droplets of water, aerosols, staying aloft for weeks or months, reflecting some sunlight, creating spectacular sunsets. One of the minor silver linings, I suppose, with vivid reds and oranges and purples as the high-altitude particles scatter light. There would be some cooling. Global temperatures might drop by a degree or 2 Celsius for a year or so. Not enough to cause widespread crop failures on a global scale. Not enough to trigger an impact winter of the sort that follows truly large impacts. But enough to affect growing seasons in some regions, especially those already at the margins. Enough to make the already difficult recovery slightly more difficult. The ozone layer would be affected, all that water vapour in the stratosphere, breaking down into hydrogen and oxygen radicals under intense solar UV radiation, interacting with ozone molecules. We'd likely see increased UV radiation reaching the surface for several years. Higher rates of skin cancer, agricultural impacts on UV-sensitive crops, manageable, but another stress on an already stressed global system. And then there's the impact site itself. In the ocean, we'd have a crater, temporary as water flows back in, but initially a massive depression, perhaps 5 to 8 kilometers across on the seafloor depending on the rock type and impact angle. Depending on the exact depth at impact, this might even temporarily expose the seafloor before water rushed back in, though we're talking about seconds here, not minutes. The surrounding ocean floor would be scoured, devastated, every living thing for hundreds of kilometers, gone, vaporized or killed by the shock wave. The deep sea ecosystems, those remarkable communities around hydrothermal vents, the cold seeps, the abyssal plains teeming with specialized life, obliterated. The ecology of the impact region would be sterilized. It would take decades for life to recolonize, for bacteria and other microbes to establish themselves, for the food webs to rebuild, for fish populations to recover. But they would recover. The ocean is vast. Life is resilient. Given time, decades, maybe a century, even the impact site would be teeming with life again, perhaps with slightly different community structures, but alive nonetheless. So let's step back and assess this scenario. The smaller impact, 440 meters. Death toll, millions, probably between 5 and 15 million, mostly from the tsunamis. Horrific. Tragic beyond measure. Each of those millions is a person, a life, a story ended. Families destroyed, communities gone. Economic damage, tens of trillions of dollars. The Pacific Rim economy is devastated. Global trade disrupted for years. Recovery taking decades. A generation that would grow up in the shadow of this catastrophe. Long-term effects, regional disruption to fisheries and ocean ecosystems, slight global cooling for a year or two, some ozone depletion, but nothing permanent, nothing that prevents recovery. Humanity survives, civilization survives. We rebuild, slowly, painfully, but we rebuild. In 100 years, the impact would be history, remembered, studied, memorialized, but not the end of human civilization. We would have recovered. It's sobering to call this the optimistic scenario, given the death toll, given the suffering it would cause, but compared to what could happen, compared to what we're about to explore in the larger impact scenario, this is survivable. And here's something worth contemplating. Impacts of this scale are rare, but not impossibly rare. We know from crater records, from geological evidence, from statistical studies of near-Earth objects, that Earth has been struck by objects this size many times in its history, roughly every few thousand years, perhaps every few tens of thousands of years, depending on your exact size threshold. We're due, in a statistical sense, for something like this eventually. Not tomorrow, probably not in our lifetimes, possibly not for thousands of years, but eventually. Which is why planetary defense matters, why we're building better detection systems like the Atlas network that found 3I Atlas, why we're developing deflection technologies like the DART mission, why we're tracking asteroids and cataloguing their orbits and developing the capability to protect ourselves. Because while a 440-meter impact would be survivable, it would also be preventable. With enough warning, years of warning, not months, we could deflect something this size. We could prevent those millions of deaths. That's worth investing in, worth preparing for, worth taking seriously. But now we need to consider the other possibility, the larger estimate for 3I Atlas, the scenario where the nucleus is not 440 meters, but 5.6 kilometers across, where the impact isn't just catastrophic, but potentially extinction level. That's what we'll explore next. And you might want to take a breath before we continue, because this is where the scenario becomes truly sobering. 5.6 kilometers of comet, moving at 60 kilometers per second, striking the Pacific Ocean. Let's see what happens when the impact enters truly apocalyptic territory. Now, we need to consider the possibility that 3I Atlas is not a relatively small building-sized object, but something far more substantial. 5.6 kilometers across, more than 10 times larger in diameter, over 1,000 times more massive. A genuine mountain hurtling through space. This is no longer a regional catastrophe. This is what geologists call a mass extinction event, the kind of event that appears in the geological record as a boundary layer, a thin line of sediment marking the moment when life on Earth fundamentally changed. To understand what we're dealing with, we need to look back 66 million years to the Yucatan Peninsula, to an event that fundamentally reshaped life on Earth and created the conditions that allowed mammals and eventually humans to evolve and thrive. The Chicxulub impactor, the asteroid or comet that ended the Cretaceous period and killed the dinosaurs, was somewhere between 10 and 15 kilometers across. Probably around 12 kilometers based on our best estimates from the crater it left behind, from the global layer of iridium and shocked quartz in the geological record, from computer simulations of the impact. 3. I-Atlas at 5.6 kilometers would be smaller than Chicxulub, perhaps half the diameter. And you might think that's reassuring. Half the size means less severe, right? But remember the velocity. Chicxulub struck at perhaps 20 kilometers per second, already catastrophically fast. 3I Atlas would be hitting at 60 kilometers per second, 3 times faster, 9 times more kinetic energy per unit of mass. So, while 3I Atlas would be smaller, the total energy release would be comparable. Not identical, but in the same terrifying category. Similar enough that the distinction would be academic to anyone experiencing it. We're talking about hundreds of thousands of megatons, maybe 500,000. The uncertainty in these calculations is large because we're extrapolating from physics that's difficult to test experimentally. You can't exactly run controlled trials of extinction-level impacts, but the order of magnitude is clear. This would be thousands of times more powerful than the smaller impact we just explored. The difference between a city destroyed and a planet transformed. So let's walk through what happens. Same scenario for consistency. Pacific Ocean impact, Central Pacific, deep water. but now with an object that's genuinely mountain-sized that would dwarf Everest if you could somehow place them side by side. The approach would be visible for longer. A 5.6-kilometre comet, developing a brilliant tail as it nears the sun, brightening dramatically, would be spectacular in the night sky for weeks before impact. Utterly beautiful and utterly terrifying. People would photograph it, track it, children would point at it, the astronomical community would be studying it intensely, refining impact predictions, understanding with growing certainty what's coming. And then it arrives. At 60 kilometers per second, the comet punches through the atmosphere in less than 2 seconds. There's barely time for atmospheric heating. The comet remains largely intact, massive enough that atmospheric drag barely affects it until it hits the water. And when it hits, the impact doesn't just vaporize water, it punches through 4 or 5 kilometers of water, gone, vaporized instantly. Then through the oceanic crust beneath, basalt bedrock, kilometers thick, shattered and vaporized, and deep into the mantle, excavating a cavity that would be impossible in any other circumstance. The crater, the initial transient crater before material collapses back, would be perhaps 50 to 80 kilometers across, an entire ocean basin excavated in seconds. For comparison, that's roughly the width of the greater Los Angeles area. The energy release is instantaneous and almost incomprehensible. Hundreds of thousands of megatons, thousands of nuclear arsenals detonating simultaneously. The fireball would rise into space, expanding beyond the atmosphere, briefly visible as a brilliant point from the moon if anyone were watching from there. The thermal pulse, the flash of electromagnetic radiation, would be lethal across thousands of kilometers. If you were standing anywhere in the Pacific Basin with direct line of sight to the impact, even from 2,000 kilometers away, the flash alone would kill you. Instant, severe burns, clothing igniting. This is before the blast wave, before the tsunami. Just the light from the explosion would be fatal across distances comparable to small countries. The seismic event would be unprecedented in human history. Magnitude 10 or higher, possibly magnitude 11. To put that in perspective, the largest earthquake ever recorded was the 1960 Valdivia earthquake in Chile at magnitude 9.5. The scale is logarithmic. Each whole number represents roughly 32 times more energy release. A magnitude 10 earthquake would be felt worldwide, not just detected on seismographs, felt. Buildings would shake on every continent. It would trigger earthquakes along fault lines globally. Every volcano that was already near eruption might be pushed over the edge. But the seismic waves would be the least of our concerns. The tsunami generated by this impact would be beyond any historical precedent. The initial wave, at the point of origin, would be over 1 kilometer high. Not a wave in the sense of something you could surf, but a moving wall of water, a translating mountain range of ocean. This wave would spread outward at 800 kilometers per hour or more in the deep ocean. As it approached coastlines, as it encountered shallow water, heights of 100 meters would be common. In some locations focused by underwater topography, the waves might reach 300 meters. That's the height of the Chrysler Building, the height of a 100-story skyscraper. Hawaii would not survive as a habitable location. The islands would be overtopped completely. Even Mauna Kea, at over 4,000 meters elevation, would be struck by massive waves. Everything would be scoured away. The islands would emerge afterward as barren rock. Japan would face waves 100 meters high, or more arriving perhaps 6 hours after impact. There is no evacuation possible that saves significant populations from this. The entire coastal plain would be inundated kilometers inland. Tokyo would cease to exist as a city. Every coastal city, Osaka, Kobe, Nagoya, Yokohama, gone. We're talking about tens of millions dead in Japan alone. The Philippines, Indonesia, all of coastal Southeast Asia, devastated. Hundreds of millions of people live in coastal regions around the Pacific. The death toll would be in the hundreds of millions. Perhaps 500 million people would die in the first day, just from the tsunamis. The western coast of North America would face similar destruction. Los Angeles, San Francisco, Seattle, Vancouver, every major city would be obliterated. The waves would penetrate tens of kilometers inland. The death toll in the United States and Canada would be in the tens of millions. But here's the terrible reality. Those killed by the tsunami would be the fortunate ones. Their deaths would be quick, relatively speaking. For those who survived the initial impact effects, for most of humanity that wasn't near the Pacific coastlines, what comes next would be worse. The impact would throw material into space, literally into space, beyond the atmosphere. Millions of tons of rock, vaporized seawater, comet fragments, all lofted on ballistic trajectories. Some would leave Earth entirely, but most would go up and then come back down. Over the following hours, this material would re-enter the atmosphere globally. All around the planet, the sky would fill with meteors. Not a few meteors, thousands of them, millions of them. Glowing trails of superheated rock falling back to Earth. And here's where things become truly apocalyptic. Each piece of re-entering ejector heats the atmosphere through friction. Collectively, millions of pieces re-entering simultaneously across the entire planet, all that kinetic energy converting to heat. The atmosphere would heat up, dramatically, rapidly. Some models suggest surface temperatures could briefly reach 300 to 400 degrees Celsius. Others suggest lower temperatures, but still well above the boiling point of water. This is the global firestorm. This is how the dinosaurs died. Anything exposed to the open sky would ignite. Forests would burst into flame spontaneously. Grasslands would burn. Wooden structures, anything combustible, all burning simultaneously, globally, within hours. The only shelter would be underwater, underground, or inside structures that could insulate against the heat. Caves would offer protection. Deep basements of stone buildings, maybe. Animals caught in the open would die. Birds would fall from the sky as the air temperature rose. Large mammals would have nowhere to hide. Even small animals, unless they were already in burrows, would perish. The extinction would be global. The fires would consume perhaps a quarter of Earth's terrestrial vegetation, maybe more. The Amazon rainforest, burning. The forests of North America, Siberia, Europe, Asia, burning. Grasslands, savannas, everything dry enough to burn, burning. The smoke and soot from these global fires would rise into the stratosphere, joining the dust and debris already lofted by the impact itself. And this is where the long-term catastrophe begins. The stratosphere would be filled with particles, dust from the pulverized rock, soot from the fires, sulfate aerosols from vaporized seawater, millions of tons of fine particles blocking sunlight. The sky would darken, not instantly, but over the course of days. Within a week, the sun would be reduced to a dim glow. Within 2 weeks, it might not be visible at all in some regions. Noon would look like twilight. This is impact winter. Temperatures would plummet. Within a month, global average temperatures would drop by 20 or 30 degrees Celsius. Within 2 months, much of the planet would be below freezing, even in tropical regions. The Amazon would freeze, and the darkness would persist. Months, certainly. possibly years depending on how much material was lofted and how quickly it settled. Without sunlight, photosynthesis stops. This is the foundation of the catastrophe. Plants die, first the small plants, the annuals, then shrubs, and eventually trees. Within months, most terrestrial plant life would be dead or dormant. In the ocean's phytoplankton, the microscopic plants that form the base of the marine food web would die first. They need sunlight. Without it, they perish within weeks. And when they die, the small animals that eat them die. And then the fish. The entire ocean food web would collapse from the bottom up. Herbivores on land would starve within weeks. Large herbivores first. Elephants need hundreds of pounds of vegetation daily. Then smaller herbivores. Then the carnivores would starve as their prey disappears. The extinction would cascade through ecosystems. This process would take months, perhaps a year, but the outcome would be certain: a mass extinction comparable to the end Cretaceous event. Perhaps 75% of all species would go extinct, maybe more. Large animals would fare worst. Anything over about 25 kilograms would have very poor survival odds. Elephants, extinct. Most large mammals, extinct. Even medium-sized mammals, deer, wolves, large cats, all gone. Birds would be particularly vulnerable. They have high metabolic rates, need lots of food. Most bird species would go extinct. The skies would be silent. Reptiles and amphibians might fare slightly better. They're cold-blooded, have lower metabolic needs. Some would survive in burrows and caves, but many species would still be lost. In the oceans, the deep sea would be a relative refuge. Deep-sea ecosystems don't depend on sunlight. They depend on chemosynthesis at hydrothermal vents. These would be disrupted, but not destroyed. Deep-sea life would survive for the most part. But surface and coastal marine ecosystems would collapse. Coral reefs would die. Coastal fish populations would crash. And then there's the question that matters most. Would humanity survive? The answer is uncertain. Possibly. It would depend on many factors. The immediate deaths, from the tsunami, the firestorm, the initial chaos, would number in the billions. Probably 3 to 5 billion people would die in the first month. The coastlines hold much of our population. The firestorm would kill anyone caught outside. But some would survive the initial catastrophe. Those in the right locations, inland, underground, sheltered. Perhaps 1 billion people would survive that first month. Then comes impact winter. Food production would stop immediately. Crops would die in the fields. Livestock would starve. Supply chains would break down. Starvation would become universal. Even with food reserves, even with strict rationing, most people would die of starvation within a year. Modern civilization depends on constant production and distribution. When that stops, starvation comes quickly. The only humans with a reasonable chance of survival would be those in very specific circumstances. Deep underground shelters with years of food supplies, with hydroponic growing facilities, powered by nuclear or geothermal energy. Submarine crews with enough supplies, perhaps some remote research stations in Antarctica. We're talking about a surviving human population of perhaps thousands, maybe tens of thousands if we're fortunate, scattered in small pockets across the planet, isolated from each other, struggling to survive year by year. And even these survivors would face enormous challenges, equipment failures, medical emergencies with no doctors, social conflicts, the psychological toll of knowing that almost everyone they ever knew was dead. That civilization had ended. Eventually, years later, perhaps a decade later, the dust would begin to settle. Sunlight would return, first as a dim glow, then brighter, eventually approaching normal levels. The planet that emerged would be transformed. Ecosystems would be in ruins, but life would begin to recover. Plant seeds that survived would germinate. Grass would grow first, then shrubs. Eventually forest would return, but it would take centuries. Animals that survived would begin to repopulate, but ecosystems would be fundamentally different. Many niches would be empty. Evolution would begin filling them, but that takes millions of years. And humans, if any survived to emerge into a recovering world, they would face a planet that was barely recognizable. No infrastructure, no power grid, no communications, just survival. They would be starting over. Stone Age conditions with some remnant knowledge of what was lost. Perhaps some books would survive, perhaps some data storage. But it would still take generations, centuries, to rebuild anything resembling civilization. This is what a 5.6-kilometer impact means. Not just destruction, not just catastrophe, but the end of the world as we know it. A mass extinction that would rival the worst events in Earth's geological history. And the sobering thing is, this has happened before. Not to humans. We weren't around 66 million years ago. But to the dinosaurs, the ammonites, the pterosaurs, all gone in an event very similar to what we've just imagined. The fossil record shows us this clearly. The difference is that we know about it. We understand the physics. We can see it coming. And with enough warning, years of warning, not months, we might be able to prevent it. But with only months of warning, with an interstellar object arriving too fast to intercept, too massive to deflect, we would be as helpless as the dinosaurs were. So let's take a breath. Step back from this scenario. Remember that this didn't happen. 3i Atlas passed safely by. This extinction event remains a thought experiment. But it's a thought experiment worth having, because it teaches us about the fragility of our world, the razor's edge we live on, and it reminds us why planetary defense matters, why we need to keep watching the sky, why we need to keep developing the technology to protect ourselves. Because the universe is not empty, and the future is not guaranteed, and the only thing standing between us and scenarios like this is our vigilance, our technology, and our good fortune. So, let's step back from the catastrophe itself and ask a more practical question. Could we actually survive? Not in the abstract, but in the specific. What would it take? What strategies might work? What are the realistic prospects for human survival in each scenario? We've already touched on this, but let's explore it more deeply. Because the answer is different depending on which impact we're facing, and understanding the difference helps us appreciate both the challenge and the possibilities. For the smaller impact, 440 meters, the answer is relatively straightforward. Yes, humanity survives. Most of humanity survives, in fact. The death toll would be in the millions, concentrated around the Pacific Rim. The economic devastation would be global and severe, but the species endures. Civilization continues. We recover. The challenge wouldn't be biological survival, it would be social, economic, and political recovery. How do you rebuild when the world's largest economies have been devastated? How do you manage the refugee crisis when hundreds of millions of people have lost their homes? How do you maintain global cooperation when resources are scarce and nations are struggling? These are difficult questions, but they're solvable. They're the kind of challenges humanity has faced before, if not quite at this scale. We've recovered from wars, from pandemics, from economic collapses. This would be worse than any of those, certainly. The worst disaster in recorded history, but not unprecedented in kind, just in scale. The infrastructure would still exist for recovery. Most of the world's farmland would be intact. The majority of agriculture happens inland, away from coastlines. Most power plants, most factories, most cities, still there. You'd have a functioning global civilization, damaged but operational, capable of reorganizing and rebuilding. Food supplies would be tight for several years. The disruption to Pacific fisheries, the contamination of coastal agricultural land by saltwater, the economic chaos affecting distribution networks, all of this would create shortages. Prices would rise dramatically. There would be hunger in some regions, particularly those dependent on coastal fishing or coastal agriculture. But not global famine, not starvation on a massive scale. With proper rationing and international cooperation, with food aid flowing from unaffected agricultural regions to affected ones, everyone could be fed. It would be uncomfortable, certainly. Diets would be restricted, variety would be limited, but survivable. The psychological impact would be profound. An entire generation growing up in the shadow of this catastrophe. Trust in the permanence of civilization would be shaken. The knowledge that we live on a fragile world, subject to cosmic forces beyond our control, would become visceral rather than abstract. But humans are remarkably resilient. We adapt. We process trauma. We rebuild. We find hope even in difficult circumstances. Children would grow up hearing stories of the impact, learning about it in school, but also seeing the recovery, witnessing human cooperation and determination. So for the smaller impact, survival isn't really in question. Recovery is the challenge, but it's an achievable challenge. Within a century, perhaps less, the world would be rebuilt. Different, certainly. Changed by the experience, but rebuilt. The larger impact, 5.6 kilometers, is a very different question entirely. Here, we're not asking, can civilization survive? We're asking, can the species survive? Can humans as a biological entity persist through years of darkness and cold? And the honest answer is, we don't know. Probably, but not certainly, it would be close. Let's think about what survival would require. Not abstract survival, not hoping for the best, but actual, practical survival through an impact winter that could last years. What would you need? What would work? What's realistic? First, you need shelter. Not just any shelter. You need protection from the initial thermal pulse, from the global firestorm that follows, and then from the months or years of cold and darkness that constitute impact winter. This means underground facilities, deep enough to provide insulation, strong enough to withstand the seismic shock. Purpose-built bunkers would be ideal. Military command centers designed to survive nuclear war. Government continuity facilities meant to preserve leadership during catastrophic events. These exist in many countries. The United States has multiple such facilities. Russia has them, China, Britain, other nations with the resources to build them. They're hardened against blast effects, against radiation, against electromagnetic pulse. They could probably withstand the thermal pulse and seismic effects of even a large impact. But here's the problem. They're not designed for years of occupation. Most have supplies for weeks or months, not years. They're meant to shelter leadership during a crisis and then emerge when it's over. For impact winter, you'd need to massively expand those supply stockpiles. Food, water, medical supplies, spare parts for critical systems. This would require advance warning and preparation. With months of warning, you could theoretically stock a bunker adequately. But it would be a massive undertaking. Natural caves could work, particularly deep ones. The Earth itself provides excellent insulation. Temperature in deep caves remains constant year-round, typically close to the average annual surface temperature of the region. During impact winter, when the surface freezes, a deep cave might remain just above freezing. Cold, certainly, but survivable with proper clothing and a heat source. Caves have been used for human shelter since prehistoric times. They're naturally protected. Some are enormous. could house significant populations. The challenge is making them livable for extended periods. You'd need to bring in supplies, set up life support, establish power generation. But it's possible. Submarine facilities might offer interesting possibilities. Nuclear submarines can remain submerged for months, produce their own oxygen through electrolysis of water, desalinate seawater for drinking. During the impact winter, the oceans wouldn't freeze. They hold too much thermal mass. Surface temperatures would drop, but the deep ocean would remain liquid. Submarines could surface occasionally. Avoid the worst of the surface conditions. Fish for whatever marine life persists. Deep sea life would survive impact winter better than surface life. It doesn't depend on photosynthesis, depends instead on chemosynthetic bacteria and the rain of organic matter from above. That rain would be disrupted, but the core deep-sea ecosystems would persist. Research stations in Antarctica, oddly enough, might be among the better locations. They're already designed for isolation, for surviving in extreme cold, for producing their own power through geothermal or nuclear means. They have greenhouses for growing fresh vegetables, life support systems designed for self-sufficiency. The impact: winter wouldn't make Antarctica much colder than it already is. It's already frozen. The main change would be the darkness, but Antarctic research stations already deal with months of darkness during the polar winter. They have artificial lighting, systems for maintaining mental health during dark periods. But shelter is just the beginning. You need food, and this is where the challenge becomes truly daunting. For a few months, stored food would suffice. Every developed nation maintains strategic grain reserves, typically enough for several months of consumption. Military bases stockpile supplies. Many individuals, particularly those who take emergency preparedness seriously, have personal stockpiles. But these wouldn't last years, not for significant populations. You'd need to grow food. Without sunlight, which means artificial light, which means power, which means either nuclear reactors or geothermal energy, or some other renewable source that doesn't depend on weather conditions. Solar is useless during impact winter. The sky is dark. Wind might work if you're on the surface with functioning turbines, but surface conditions would be brutal, and maintaining equipment would be difficult. Hydroelectric requires flowing water, which requires precipitation, which requires a functional water cycle, disrupted during impact winter. Nuclear power is the most reliable option. A nuclear reactor can run for years without refueling if properly managed. The French nuclear industry has demonstrated refueling cycles of 18 months or more. With careful management, you could stretch that longer. And nuclear reactors have been miniaturized. Small modular reactors exist that could power a shelter facility. But you'd need the technical expertise to maintain it, the spare parts for repairs, the cooling water, and you'd need to convert that power into food through hydroponic or aquaponic systems. Hydroponics is growing plants in nutrient solution without soil. It's more efficient than traditional farming in many ways, uses less water, less space, can be stacked vertically in controlled environment facilities. NASA has researched it extensively for long-duration space missions. The International Space Station grows some of its own fresh vegetables hydroponically, but it requires careful management. The nutrient ratios must be precise. Plants need nitrogen, phosphorus, potassium, plus trace elements like iron, magnesium, calcium. The pH must be monitored and adjusted. Most plants prefer slightly acidic conditions. The plants need proper lighting. Grow lights that simulate sunlight's spectrum and intensity. Temperature and humidity must be controlled. In principle, a facility with nuclear power and well-designed hydroponic systems could sustain a population indefinitely. In practice, it's extraordinarily difficult. Any breakdown in the system, a pump failure, a nutrient imbalance, a disease affecting the plants, could be catastrophic when there's no redundancy, no backup, no external sources of food. You'd need more than just calories too. You'd need complete nutrition. Vitamin deficiencies would become serious within months. Scurvy from lack of vitamin C, historically a problem for sailors on long voyages. Beriberi from lack of thiamine. Rickets from lack of vitamin D, though that's actually produced by sunlight exposure, so you definitely need supplements during underground life. You'd need to grow a variety of crops, not just staples like wheat or rice, or supplement extensively with stored vitamins, which have limited shelf life. A truly self-sufficient facility would need to grow leafy greens for vitamins, legumes for protein, perhaps fruit if space and energy allowed. Protein would be a particular challenge. Plants provide protein, but often not complete proteins with all essential amino acids. Beans and rice together provide complete protein, but you'd want more variety. You'd want fish from aquaponics systems, growing fish and plants together. The fish waste fertilizing the plants filtering the water for the fish. Tilapia is commonly used. It's hardy, grows quickly, tolerates a range of conditions. Let's talk about population and scale, because the numbers matter enormously. A nuclear submarine has a crew of about 150 people, give or take depending on the class. That's with very limited space, very efficient systems, and resupply assumed at regular intervals. Could you support 150 people for 5 years in a submarine? Probably not without surfacing regularly for food. The submarine's oxygen generation and power systems could theoretically work indefinitely, but food storage is the limiting factor. A large underground facility, say the size of a major government bunker, might house 1,000 people comfortably. Feed them with stored food for a year, maybe 2 if strictly rationed. But growing enough food hydroponically for 1,000 people would require enormous space, massive amounts of power, and flawless execution. Some calculations suggest you'd need about 100 square meters of growing space per person for complete nutrition using efficient hydroponic systems. That's being fairly optimistic, assumes vertical farming, multiple harvests per year, efficient varieties. For 1,000 people, that's 100,000 square meters of growing space, 10 hectares, about 25 acres of underground greenhouses. That's a lot of space to excavate, light and maintain. That's a lot of power. The grow lights alone would consume enormous amounts of electricity. And remember, this is just for food. You also need living space, machinery space, water storage and treatment, waste processing and recycling. A truly self-sustaining bunker for 1,000 people would be an enormous facility. So realistically, we're probably talking about smaller populations per facility. Maybe 100 people in a well-equipped facility. Maybe a few hundred in the largest, best-equipped locations like major military installations or purpose-built survival complexes. How many such facilities exist or could be rapidly converted? It's hard to say with certainty. Governments don't publicize these details, but we can estimate. Government continuity bunkers exist in many countries. Military command centers. Some private bunkers built by wealthy individuals, more common than you might think. Research stations in Antarctica. About 70 permanent research stations housing a few thousand people total during summer. Fewer during winter. If we're generous, maybe a few hundred facilities worldwide could potentially support populations through impact winter. Maybe each could support an average of 100 people, though most would be significantly smaller. That gives us perhaps tens of thousands of people globally. maybe 100,000 at the absolute maximum if everything goes right. But that assumes everything does go right, that every facility has time to stock up, that the people who make it to these facilities are the right mix. You need engineers to maintain systems, doctors for medical care, agricultural specialists for food production, not just politicians and billionaires. That the facilities don't suffer catastrophic failures, that the populations don't tear themselves apart through social conflict. Realistically, the survival rate would probably be lower, perhaps a few thousand people worldwide, maybe 10,000 if we're fortunate, and if there was adequate preparation time. Compare this to a global population of 8 billion. We're talking about a survival rate of perhaps 1 in a million, perhaps 1 in 800,000 if we're optimistic. Those are sobering odds, extinction-level odds for individuals, though probably not for the species. And even these survivors would face immense ongoing challenges. Let's imagine you're one of the fortunate few. You're in a bunker, underground, with food and power. The impact winter has begun. Years of darkness and cold stretch ahead. The first major challenge is psychological. You're trapped underground for years. You can't go outside. The surface is frozen, dark, lethal. You're with the same small group of people day after day after day. The boredom would be crushing, the monotony, the lack of privacy, the knowledge that everyone you knew outside the bunker is probably dead. Studies of people in isolated conditions, Antarctic research stations, submarine deployments, the International Space Station, show that psychological health is often the limiting factor. People need mental stimulation, social variety, purposeful activity, hope for the future. Depression becomes common, conflicts arise, in extreme cases, violence. Now multiply these stresses by the duration, not 3 months like a typical submarine deployment, not a year like an ISS mission, but years, multiple years, and add the knowledge that you're among the last humans alive, that there's no rescue coming, that the world you knew is gone. The second challenge is maintaining complex systems with limited resources. Your hydroponic systems need continuous maintenance. Pumps fail, lights burn out. You have spare parts, but they're finite. Once they're gone, you're improvising repairs with whatever you can scavenge or fabricate. Your nuclear reactor needs skilled maintenance. It's designed to run for years, but it still needs attention. Cooling systems, control systems, radiation shielding. If something goes seriously wrong, do you have the expertise to fix it? The tools, the replacement parts? Medical issues would be inevitable. Appendicitis, broken bones, dental problems, infections. Without proper medical facilities and trained doctors, these could be fatal. You'd have antibiotics, but they have expiration dates. Surgery without proper equipment and sterile conditions would be extremely risky. And then there's social cohesion. In a small, isolated group, conflicts become magnified tremendously. Personality clashes that would be minor annoyances in normal society become existential threats when you literally can't get away from each other. Leadership disputes, resource allocation disagreements, romantic entanglements and their inevitable complications. You'd need strict social structures, clear rules, effective mechanisms for conflict resolution. The groups most likely to survive would be those with strong, fair leadership, shared purpose and culture that emphasized cooperation over competition. But assuming you navigate all these challenges, assuming your bunker survives, your systems keep working, your group stays cohesive, eventually the dust settles, the sky clears, sunlight returns. Years have passed, but it's finally safe to emerge. What do you find? a world transformed. The surface would be frozen initially, covered in snow and ice in most regions. But as sunlight returns, warming begins. Slowly, the ice melts. Temperatures rise. The water cycle restarts. Weather patterns return. Plant life would begin to recover wherever seeds survived. Seeds can remain viable for remarkably long times under the right conditions. First grasses would appear, then shrubs. Areas that remained slightly warmer, volcanic regions, geothermal areas, might have preserved small pockets of plant life that could spread and recolonize. Animal life would be sparse. Small mammals that sheltered in burrows might emerge. Some bird species might have survived in protected locations. Deep sea life would have persisted throughout and could recolonize shallower waters. But large animals would be gone, the megafauna extinct. You'd be emerging into a world that's ecologically young, an empty world in many ways, in a sense, starting over. The survivors would need to transition gradually from bunker life to surface survival. You wouldn't abandon your shelter immediately. You'd scout cautiously, test the conditions, start growing food outside in experimental plots, eventually move out fully when confident it's safe. And this is where the long-term survival of humanity would really be determined. Could these scattered groups of survivors maintain their technology? Could they reconnect with other survivor groups? Could they maintain genetic diversity, critical for long-term species survival? With thousands of survivors scattered globally, probably yes. Different groups would eventually find each other as communication infrastructure was rebuilt. Over generations, they'd rebuild, slowly, starting from a much smaller population, with much of the technical knowledge preserved in books and data storage, but much of the practical infrastructure gone. With only a few hundred survivors, or survivors concentrated in just a few locations, it becomes more uncertain. Genetic diversity would be limited. Inbreeding would become a serious problem within a few generations, leading to genetic disorders and reduced fitness. Technical knowledge might be preserved theoretically, but lost practically without the infrastructure to apply it. The recovery would take centuries at minimum, possibly millennia. You'd be starting from small communities with some retained knowledge, but essentially Stone Age material conditions, eventually working back up through agriculture, metallurgy, machinery, industrialization, but with the advantage of knowing it's possible, knowing the principles, having some preserved texts and data to guide you. It would be a very different world, different cultures emerging from the survival groups, different languages perhaps, or at least dialects, different values shaped by the trauma of near extinction and the challenge of survival and rebuilding. But recognizably human, still us, still continuing, still building toward something. So could humanity survive a 5.6-kilometre impact? Probably yes as a species, though the odds for any individual would be poor. But what we'd lose, the art, the literature, the accumulated knowledge of thousands of years of civilization, the 8 billion lives and their stories, would be incalculable and irreplaceable. And this brings us back to why planetary defense matters so profoundly. Because while survival is possible in principle, it comes at a cost so extraordinarily high that prevention is infinitely, immeasurably preferable. A 440-metre impact, preventable with current technology if we have years of warning, worth significant investment to avoid. A 5.6-kilometre impact, probably beyond our current deflection capabilities, but detectable with enough advance warning that we could at least prepare. Or, given decades of warning instead of months, we might develop the capability to deflect even something this massive. The key is time. Time to detect, time to analyze, time to respond. This is why we need better telescopes, better detection networks, better tracking of near-Earth objects, and yes, even interstellar visitors. Because 3i Atlas passed safely by, but other objects will come. Statistics suggest one interstellar object passes through our inner solar system every year or two. Most are small, most pass harmlessly at safe distances, but eventually, maybe in 100 years, maybe in 1,000,000, another will arrive on a trajectory that threatens us. And when that happens, we want to be ready. We want to have the technology, the infrastructure, the international cooperation necessary to respond effectively. We want the detection systems that give us years or decades of warning instead of months. We want the deflection capabilities that turn a certain catastrophe into a successful planetary defense. That's the real lesson here. Not fear, but preparedness. Not panic, but prudent precaution. Understanding the risks so we can rationally invest in mitigating them. Now let's turn our attention to what makes an interstellar impact fundamentally different from an asteroid or comet from our own solar system. Because 3i Atlas isn't just another space rock, it's a visitor from beyond, and that changes things in important ways. The most obvious difference, the one we've been emphasizing throughout, is velocity, speed. This matters more than almost anything else when it comes to impact physics. Let's establish some baselines for comparison. Objects that belong to our solar system, asteroids, comets, everything that's gravitationally bound to the Sun, move at speeds determined by their orbital dynamics. The physics are well understood, predictable, governed by Kepler's laws and Newton's equations. Earth orbits the Sun at about 30 kilometers per second. We're moving quite briskly through space, though it doesn't feel that way from our perspective. An asteroid in a typical near-Earth orbit might approach us at anywhere from 11 to about 25 kilometers per second, depending on whether it's catching up with Earth from behind or meeting us head-on in our orbital path. The relative velocity depends on the geometry of the encounter. If an asteroid is orbiting the Sun in roughly the same direction as Earth, but in a different orbit that crosses ours, the closing speed might be relatively low, perhaps 11 or 12 kilometers per second. Still devastatingly fast by any normal measure, but on the lower end for cosmic collisions. If an asteroid approaches from the opposite direction, retrograde, orbiting the Sun backward relative to Earth, the velocities add up. Earth's 30 kilometers per second plus the asteroid's orbital velocity could result in impact speeds of 40 or even 50 kilometers per second in extreme cases. Comets from the Oort cloud, those icy visitors from the distant reaches of our solar system, are typically faster than asteroids. They're falling inward from enormous distances, tens of thousands of astronomical units, building up speed as they approach the Sun. By the time they reach Earth's orbit, they might be travelling at 40 kilometers per second or more, maybe 45 in extreme cases. These are already terrifying speeds. A 40 kilometer per second impact carries enormous energy. The Tunguska event, the Chicxulub impact, both involved objects moving at these sorts of velocities, perhaps slightly slower in Tunguska's case, similar or slightly slower for Chicxulub. But 3i Atlas is moving at 60 kilometers per second, 50% faster than even the fastest solar system comets. And remember that crucial relationship, kinetic energy scales with the square of velocity. 50% more speed means 2.25 times more energy per unit of mass. Actually, if we're comparing 60 to 40, that's 1.5 times the velocity, which squares to 2.25 times the energy. The math gets frightening quickly. This isn't a small difference. This is the difference between catastrophic and substantially more catastrophic. It's the difference between a city destroyed and a region devastated, between millions dead and tens of millions. The velocity matters immensely. Why is 3i Atlas moving so fast? Because it's not bound to our Sun. It's not in a gravitationally closed orbit. It's passing through. It arrived with the velocity it gained from wherever it came from. Some other star system, some other gravitational environment, plus whatever additional velocity it picked up, falling through our Sun's gravity well as it entered the inner solar system. But crucially, it's not slowing down to stay. It's not being captured. Its trajectory is hyperbolic, not elliptical. A one-way trip, in and out. The Sun's gravity bends its path slightly, changes its direction, but doesn't capture it. So it maintains that tremendous interstellar velocity, that excess speed that marks it as a visitor rather than a resident. From a defensive standpoint, this velocity presents enormous challenges. Let's think carefully about deflection and why it becomes so difficult. The DART mission in 2022 successfully demonstrated asteroid deflection, and it was genuinely remarkable. We sent a spacecraft to intercept the asteroid Dimorphos, a small moon of the larger asteroid Didymos, about 160 meters across. The spacecraft struck at about 6 kilometers per second relative velocity. The impact changed Dimorphos's orbital period by about 33 minutes, more than expected actually, which was encouraging. It was a triumph of planetary defense, proof that we can alter the trajectory of threatening objects. But consider the timeline. DART launched in November 2021 and impacted in September 2022, nearly a year of flight time, and Dimorphos was in a predictable orbit, moving at predictable speeds, following a path we could calculate years in advance. We could launch when it was convenient, navigate carefully, arrive exactly when planned. An interstellar object is fundamentally different. By the time we detect it, it's already here, already in the inner solar system, already committed to its trajectory through our neighbourhood. We'd have months at most to respond, more likely weeks or even days depending on when we first spot it and from what angle it approaches. Launching an interceptor mission in that time frame would be challenging even if the target were moving slowly. But at 60 kilometers per second, the closing velocity would be enormous. If you're launching a spacecraft from Earth to intercept it, you might need to achieve velocities of 30 or 40 kilometers per second just to catch up, depending on the geometry. The targeting would need to be extraordinarily precise. At these speeds, even small errors in position or timing translate into missing by thousands of kilometers. And even if you hit it, even if you manage to intercept it successfully, would the deflection be enough? Think about the physics carefully. DART's impact changed Dimorphos's velocity by a few millimeters per second, probably around 2 or 3 millimeters per second, based on the orbital period change. That's enough when you have months or years for that tiny change to accumulate into a significant course correction. Over a year, a change of 2 millimeters per second adds up to about 63,000 kilometers, enough to turn a hit into a miss. But with weeks of warning, even if you changed 3i Atlas's velocity by a few meters per second, far more than DART achieved, requiring a much larger impactor or multiple impacts, it might not be enough deflection to turn a direct hit into a miss. You'd need to change its course by thousands of kilometers in just weeks. The math doesn't work out favorably. Nuclear deflection might be more effective in theory. Detonate a nuclear weapon near the object's surface, not on the surface, which might just fragment it, but nearby. The radiation vaporizes part of the surface. The expanding vapor creates thrust, pushes the object off course. In principle, this could provide much more deflection than a kinetic impactor, possibly changing the object's velocity by tens or even hundreds of meters per second. But again, you need time. Time to launch, time to intercept, time for the deflection to accumulate into sufficient course change. And nuclear weapons add layers of complexity, international treaties that would need to be navigated, political considerations about who launches nuclear-tipped rockets, the technical challenge of detonating a nuclear device in space with precise timing and positioning. With years of warning, deflection might be possible. We'd have time to develop a mission profile, to build the spacecraft, to launch multiple attempts if necessary, to verify the deflection was working. With months, probably not sufficient time, we'd be watching it approach, calculating the impact point with increasing precision, and finding ourselves unable to stop it. This is fundamentally different from our current planetary defense paradigm. We've built our systems, our strategies, our planning around the assumption that we'll track objects for years or decades before they threaten us, that we'll have time to observe, to refine orbits, to mount a deflection mission, to verify success. Interstellar objects break that assumption entirely. Then there's the composition issue, which is scientifically fascinating and practically significant. Comets versus asteroids, interstellar chemistry versus solar system chemistry. 3I Atlas is definitely a comet. We know this with certainty because we can see the coma, the tail, the activity as it approaches the Sun. It's outgassing dramatically, which means it contains volatiles, ices that sublimate when warmed by sunlight. Water ice, carbon dioxide ice, methane, ammonia, other frozen compounds. But it's an interstellar comet, formed around a different star. It formed in a different stellar nebula, with a different initial mix of elements, under different conditions billions of years ago. The chemistry is alien. Not alien in the science fiction sense. We're still talking about the same basic elements found throughout the universe, the same physics and chemistry. But alien in the literal, precise sense, from another star system, formed under different circumstances. The visible evidence of this is that distinctive reddish colour. That particular hue comes from complex organic compounds, long-chain carbon-based molecules that have been irradiated by cosmic rays during billions of years drifting through interstellar space. The radiation breaks chemical bonds, creates new compounds through radiolysis, produces that characteristic coloration we observe. These organics aren't just interesting scientifically. They would affect impact physics in measurable ways. Organic compounds vaporize and burn differently than simple water ice or silicate rock. During impact, when everything is heated to plasma temperatures, they'd still leave their chemical signature. They'd contribute differently to the atmospheric effects, to the chemistry of the debris injected into the stratosphere, to the composition of the impact plume. The isotope ratios would be different too. Every star has a slightly different composition based on its history and the cloud from which it formed. Our Sun is about 71% hydrogen, 27% helium, 2% heavier elements by mass. Other stars have similar ratios but with variations. A star formed from a cloud slightly enriched in heavy elements, perhaps from a nearby supernova, would produce comets with measurably different isotope ratios. If 3I/Atlas hit Earth, future geologists studying the impact layer would find anomalies, unusual isotope ratios of carbon, nitrogen, oxygen, trace elements in unexpected proportions, chemical signatures that don't match anything else from our solar system, clear evidence of interstellar origin preserved in the geological record for millions of years. This has actually happened before, by the way. Not recently, not in human history, but in Earth's deep past. Some researchers have suggested that certain anomalies in ancient geological layers, unusual isotope ratios, Peculiar concentrations of certain elements might indicate ancient interstellar impacts. It's controversial, not widely accepted, but intriguing. The idea that Earth might have been struck by interstellar objects in the distant past, leaving subtle chemical traces we're only now learning to recognize and interpret. Let's talk about detection specifically. How do we find these objects? How much warning do we typically get? For solar system asteroids and comets, we have extensive, sophisticated tracking programs. Pan-STARRS in Hawaii, scanning large patches of sky nightly. The Catalina Sky Survey in Arizona with multiple telescopes. The ATLAS system that found 3i Atlas, a network of telescopes designed specifically to find potentially hazardous objects. These programs scan the sky repeatedly, comparing images from night to night, looking for anything that moves against the fixed background of stars. When they find something new, they calculate its orbit. If the orbit brings it near Earth, we track it carefully, refine the predictions with additional observations, and determine whether it poses any threat. Years in advance, we know if something might come close. Decades in advance for the largest objects. We've catalogued about 90% of near-Earth asteroids larger than 1 kilometre. We know where they are, where they're going, when they'll pass close to Earth. None currently threaten us for the foreseeable future. This is a remarkable achievement in planetary defence. But interstellar objects come from random directions. They're not confined to the ecliptic plane where most solar system objects orbit. They can come from literally anywhere in the three-dimensional sky. This makes them much harder to find. There's more sky to search, and they're only visible for a brief period as they pass through the inner solar system. 3i Atlas was detected on July 1st, 2025. It passed through the inner solar system over the following months, brightening as it approached the Sun, then fading as it departed. If it had been on a collision course with Earth, we probably would have had 3 to 6 months of warning, maybe more if we were very lucky and spotted it early in its approach. Maybe less if the approach angle was unfavourable, if it came from the direction of the Sun where we can't easily observe, or if it was smaller and fainter than it turned out to be. Compare this to asteroid Apophis, a useful example. We've been tracking Apophis since its discovery in 2004. We know its orbit precisely now. We know it will pass very close to Earth in 2029, closer than our geostationary satellites, just 31,000 kilometres from Earth's surface, close enough to be visible to the naked eye as it passes. But we also know with absolute certainty that it won't hit us. Not in 2029, not in the foreseeable future. The calculations are that precise. With an interstellar object, we don't have that luxury. We find it. We calculate its trajectory as best we can with limited observations. We realize it's going to hit or pass close, and we have months at most to prepare, but not years to prevent. This changes everything about how we'd respond to the threat. You can't evacuate entire coastlines with just months of warning. Well, you can try, but it would be chaotic, incomplete, and many would choose not to believe until too late. You can't build underground shelters in months. You can't develop and launch a deflection mission from scratch. What you can do is prepare as best you can with existing infrastructure. Stock existing shelters with years of supplies. Evacuate the most threatened regions and hope people cooperate. Preserve knowledge in hardened facilities. Document everything. Move genetic material. Seeds, cultural artifacts to protected locations. Hope that enough people and infrastructure survive to rebuild. It's sobering, and it emphasizes why better detection is so fundamentally important. The earlier we spot an incoming object, the more options we have. If we could detect interstellar objects farther out, say when they cross the orbit of Jupiter or even Saturn, rather than when they're already in the inner solar system past Mars, we'd gain months of additional warning time, possibly enough to make deflection feasible, or at minimum to allow much better preparation. This is one reason why NASA and other space agencies are investing heavily in better telescopes, larger mirrors to see fainter objects at greater distances, infrared sensors to detect things we can't see in visible light because they don't reflect enough sunlight, space-based telescopes that can search the entire sky without being limited by weather, daylight, or atmospheric distortion. The Vera Rubin Observatory in Chile, conducting the legacy survey of space and time, will dramatically improve our ability to detect small, distant objects when it becomes fully operational. It will scan the entire visible sky every few nights. Anything that moves will be flagged automatically. Anything unusual will be investigated. It should find many more interstellar objects, giving us better statistics on their frequency and characteristics. But even with the best detection systems we can envision, interstellar objects will always present special challenges. They move too fast. They arrive from unpredictable directions. They give us limited warning time by their very nature. They're fundamentally different from the threats we've been preparing for. There's something else worth considering carefully. Frequency. How often do these objects actually arrive? We've now confirmed 3 interstellar objects passing through our solar system. Oumuamua in 2017, Borisov in 2019, and 3I Atlas in 2025. 3 in 8 years. That might seem like a lot, but remember, these are just the ones we detected. Based on this detection rate, and accounting for our observational limitations, the objects we probably missed because they were smaller, fainter, or approached from unfavorable angles, astronomers estimate that roughly 1 interstellar object passes through the inner solar system per year on average. Most are small, most pass at safe distances. The solar system is vast, Earth is tiny, and hitting us requires a very specific trajectory. The odds of any particular interstellar object striking Earth are extraordinarily low, probably less than 1 in a billion for any given object. But over geological time, over millions and millions of years, eventually the statistical odds catch up. It becomes not a question of if, but when. Statistical models, extrapolating from crater records and interstellar object frequencies, suggest that Earth might be struck by an interstellar object once every few million years. Maybe more often, maybe less. The uncertainties are large because we're working with small sample sizes and long time scales. But the essential point is clear. It's not impossible. It's not even improbable over long enough time frames. It's essentially inevitable, just rare enough that humans haven't experienced it in our brief evolutionary history. And there's another consideration, the distribution of sizes. Most interstellar objects are probably small, a few meters, a few tens of meters across. These would burn up in the atmosphere or create small impacts like Tunguska. Interesting scientifically, potentially dangerous locally if they hit a populated area, but not globally catastrophic. Large objects, kilometers across, are presumably much rarer. They're ejected less frequently from planetary systems because it takes more energy to eject a large object to escape velocity. They're harder to accelerate to the necessary speeds, but they're not impossible. 3I Atlas, at its largest estimate, 5.6 kilometers, proves conclusively that large interstellar objects exist and can pass through our solar system. So we have a situation where most interstellar objects are harmless, but occasionally, very rarely, on human timescales, a large one comes through. And when it does, we have limited time to respond and limited capability to deflect it. This is different from the asteroid threat, where large objects are rare but detectable years or decades in advance, giving us time. It's different from the comet threat, where objects can appear relatively suddenly from the Oort cloud, but at least they're moving at solar system speeds and following gravitational rules we thoroughly understand. Interstellar objects are their own category. Fast, unpredictable in timing and direction, giving limited warning, and potentially carrying enormous energy due to their velocity. Understanding this helps us appreciate what we're dealing with. It helps us plan better detection strategies tailored to this specific threat. It helps us think about what kinds of deflection technologies might work with limited warning time, perhaps pre-positioned interceptors, perhaps faster developing mission profiles. It helps us understand both the risks and the limitations of our current capabilities. And it helps us appreciate the profound gift of 3i Atlas passing safely by, because it truly could have been different. A few degrees of variation in trajectory, a slightly different angle of approach billions of years ago, when it was ejected from its home system, and instead of a fascinating astronomical observation that advanced our understanding, we'd have faced an unprecedented crisis. The universe is not empty. The space between stars is not truly empty. It's filled with wandering objects, orphaned from their home systems, travelling for billions of years through the cosmic dark. Sometimes they visit us. Usually they pass harmlessly through our neighbourhood. But not always. And the difference between harmless passage and catastrophic collision can be measured in degrees of arc, in tiny variations in trajectory determined by gravitational nudges millions of years ago. This is why we watch. This is why we calculate. This is why we prepare. Because the universe is vast and mostly empty, but not completely empty, and the objects that wander through the darkness between stars occasionally pass through our neighbourhood, reminding us that we're part of a larger, dynamic cosmos. 3i Atlas taught us a great deal about interstellar chemistry and how comets form in other stellar systems, about comet behaviour and activity, about the frequency and characteristics of these cosmic visitors. It was a gift of knowledge, arriving from beyond, staying briefly to be studied, and then departing back into the interstellar dark. But it also reminded us of our vulnerability, of the fact that we're not isolated in the universe, that we're connected to larger processes, to galactic dynamics, to the ejection and wandering of objects between stars, that what happens light years away can eventually affect us here. Let's take a step back from hypothetical scenarios and look at what has actually happened, Earth's history with cosmic impacts, the craters that mark our planet, the events we've witnessed, the near misses that remind us how fortunate we've been. Because this isn't just theoretical. Impacts have shaped Earth's history profoundly. They've caused extinctions, altered climates, influenced evolution. We exist in part because of impacts, both the ones that happened and the ones that didn't. The most famous impact, the one everyone knows about, is Chicxulub. 66 million years ago, an object somewhere between 10 and 15 kilometers across struck what is now the Yucatan Peninsula in Mexico. The impact created a crater about 180 kilometers in diameter, one of the largest impact structures on Earth. You can't see it directly from the surface anymore. 66 million years of erosion, sedimentation, and geological activity have buried it. But it's there, detectable through gravity measurements, through drilling cores that bring up shocked quartz and impact melt, through the distinctive ring structure visible in geological surveys. The impact itself was catastrophic locally. Everything within hundreds of kilometers simply ceased to exist. Vaporized, incinerated, destroyed instantly. The impact triggered massive earthquakes, magnitude 10 or higher. Tsunamis hundreds of meters high swept across the Proto-Caribbean and into the ancient Atlantic, leaving deposits of jumbled debris that we can still find in the geological record. But the global effects are what made it a mass extinction event. The dust and debris lofted into the stratosphere, blocking sunlight. The global firestorms from re-entering ejecta heating the atmosphere. The impact winter that lasted for years, perhaps decades. The collapse of photosynthesis and the subsequent collapse of food webs from the bottom up. About 75% of all species went extinct. Not just the dinosaurs, though they're the ones we remember, the ones that capture imaginations, but also countless other species. Marine life, the ammonites that had thrived for hundreds of millions of years, gone. Flying reptiles, the pterosaurs, gone. Many plant species, entire ecosystems restructured themselves in the aftermath. And yet, something survived. Small mammals, which had been minor players in the age of dinosaurs, living in the shadows of giants, suddenly found themselves in a world with empty niches, without large predators hunting them, without dominant herbivores competing for resources. They diversified rapidly. Within a few million years, a blink in geological time, mammals had filled many of the ecological roles dinosaurs once occupied. Eventually, primates evolved. Eventually, humans. We exist because the dinosaurs didn't survive, because that impact, terrible as it was for the species that lived through it, created opportunities for others, including eventually us. There's a certain cosmic irony in that. We're here, studying impacts, worrying about future impacts, building systems to prevent them, in part because an ancient impact cleared the way for our evolution. We're the descendants of the survivors, and we're trying to ensure we remain survivors. But Chicxulub isn't the only major impact in Earth's history, not even close. The geological record preserves evidence of many others, though most are far older and harder to study. The Vredefort crater in South Africa is about 2 billion years old and roughly 300 kilometers in diameter, one of the largest confirmed impact structures on Earth, though it's heavily eroded and deformed. The impactor was probably 10 to 15 kilometers across, similar to Chicxulub. It struck when Earth was young, when the atmosphere was different, when life was still simple single-celled organisms. No mass extinction in the sense we usually think of it. There wasn't enough biological complexity yet for the concept to have much meaning. But it certainly affected the local environment dramatically, and probably had global climate effects. The Sudbury Basin in Ontario, Canada, is about 1.8 billion years old. Originally about 260 kilometers in diameter, though it's been stretched and deformed by nearly 2 billion years of geological processes. The impact melted vast quantities of rock, and ironically, that melting concentrated valuable minerals: nickel, copper, platinum, gold. The Sudbury Basin is now one of the world's major mining regions. An ancient catastrophe turned economic resource. We extract wealth from the scar of an impact that occurred when Earth was barely older than a third of its current age. More recently, relatively speaking, there's the Chesapeake Bay impact crater. About 35 million years ago, an object roughly 3 kilometers across struck what is now the eastern United States. The crater is about 90 kilometers in diameter, buried beneath the Chesapeake Bay and surrounding areas. It affected the local geography, influenced the formation of the bay itself. The unique shape of the Chesapeake is partly due to settling over this ancient crater. It probably caused regional extinctions, disrupted local ecosystems, but it wasn't large enough to trigger global effects. By this time, mammals were well established, and they survived. These ancient impacts are difficult to study. Erosion obscures them. Plate tectonics deforms them, sometimes dramatically. Younger rocks bury them, but we can find them through careful geological detective work, looking for circular structures in gravity maps, searching for shocked minerals that only form under extreme pressure, analysing the chemistry of rock layers, and each one tells a story about Earth's violent past. Then there are the more recent events, recent in geological terms, thousands of years rather than millions. These we can study more directly. Meteor Crater in Arizona is perhaps the best preserved impact crater on Earth. About 50,000 years ago, recent enough that human ancestors were already walking the Earth, though not yet in North America. An object roughly 50 meters in diameter struck. It was made of iron and nickel, traveling at perhaps 12 kilometers per second. It exploded with the force of about 10 megatons, creating a crater roughly 1.2 kilometers across and 170 meters deep. The crater is beautifully preserved because Arizona is dry, minimal erosion, no vegetation to obscure it, no glaciers to scour it away. You can stand on the rim and see the entire structure clearly, the raised rim, the bowl-shaped depression, the blanket of ejected material surrounding it. It's a reminder of what even a relatively small impact can do. A 50-meter object creating a crater visible from space. The impactor was only 50 meters across. Compare that to the 440-meter scenario we explored earlier, and you begin to appreciate the scaling. The meteor crater impact was perhaps 1/100th the energy of our smaller 3 I/Atlas scenario. And it created this. Now imagine something 100 times more energetic. Now let's talk about events in recorded history, impacts that humans have witnessed, documented, and survived. The Tunguska event in 1908 is the most significant impact in modern times. On June 30th, early in the morning, a small asteroid or comet fragment, estimates suggest 50 to 60 meters in diameter, entered the atmosphere over Siberia. It exploded in the air before reaching the ground, probably at an altitude of 5 to 10 kilometers. The explosion flattened about 2,000 square kilometers of forest. 80 million trees knocked down in a radial pattern, spreading outward from the blast center. Eyewitnesses from hundreds of kilometers away described a brilliant fireball moving across the sky, then an explosion. A blast wave that knocked people off their feet, shattered windows, and was heard thousands of kilometers away. The seismic shock was detected across Eurasia. The atmospheric pressure waves circled the globe multiple times. Fortunately, it occurred in a sparsely populated region of Siberian taiga. If it had exploded over a city, if it had arrived just a few hours later when Earth's rotation had moved a populated area into its path, the death toll would have been catastrophic. Hundreds of thousands dead, possibly millions depending on the city. But as it was, only a few people were injured, primarily from the shock wave breaking windows and knocking people off their feet in settlements tens of kilometers away. The explosion was equivalent to roughly 10 to 15 megatons, similar to a large thermonuclear weapon, larger than any weapon actually used in warfare. The shockwave circled the Earth multiple times, detected on barographs around the world. The night skies over Europe and Asia were unusually bright, for several nights afterward, as dust in the upper atmosphere scattered sunlight. What's particularly striking about Tunguska is that we had absolutely no warning, no detection, no prediction. Just a bright flash, a massive explosion, and then confusion about what had happened. It took scientific expeditions years to reach the site. The taiga is remote, difficult to access. And when they arrived, they found no crater, which initially confused them. They were looking for an impact site. Eventually they realized it had been an airburst, an explosion before the object reached the ground. In 1908, we had no capability to detect incoming objects. No telescopes scanning for asteroids, no warning systems. We were simply fortunate it struck a remote area. A few hours of difference in timing, and it could have been over St. Petersburg or Berlin or London. More recently, in 2013, we had the Chelyabinsk meteor. On February 15th, an asteroid about 20 meters in diameter entered the atmosphere over Russia, specifically over the Ural Mountains region. It exploded at an altitude of about 30 kilometers, with the force of roughly 500 kilotons, much smaller than Tunguska, but still significant. Still equivalent to dozens of Hiroshima bombs. The shockwave broke windows across the city of Chelyabinsk and surrounding areas. About 1,500 people were injured, mostly from broken glass and flying debris. Many people had seen the bright trail in the sky, a magnificent fireball, and rushed to windows to watch, not realizing that a shockwave was coming, not understanding the physics of what they were seeing. When it arrived, windows shattered inward. Most injuries were minor cuts and bruises, but some were serious. It was a sobering reminder that even small impacts can harm people. What's particularly notable about Chelyabinsk is that, like Tunguska, we had no warning whatsoever. The asteroid approached from the direction of the Sun, where our detection systems have a blind spot. We can't observe in that direction because the sunlight overwhelms the telescopes, and it was relatively small, only 20 meters below the size threshold we typically track carefully with our limited resources. We simply didn't see it coming. By remarkable coincidence, that same day, a larger asteroid called 2012 DA14 made a close approach to Earth, passing just 27,700 kilometers from the surface, closer than geostationary satellites. But we knew about that one. We'd been tracking it for over a year. We knew it would miss. We knew exactly when and where it would pass. The one that actually hit, the Chelyabinsk meteor, was a complete surprise. 2 asteroids, same day, one predicted and harmless, one unpredicted and damaging. The irony was not lost on the scientific community. This illustrates an important point. Our detection systems have improved dramatically over the past few decades, but they're not perfect. Small objects can still slip through, especially if they approach from unfavorable angles or are simply too faint to detect until they're very close. Let's talk about near misses, objects that passed close but didn't hit, because these happen more often than most people realize. In 2029, asteroid Apophis will pass just 31,000 kilometers from Earth's surface. That's close enough to pass between Earth and some of our geostationary satellites, which orbit at about 36,000 kilometers. It will be visible to the naked eye from some locations, a bright point moving across the sky over the course of hours. For amateur astronomers, it will be a spectacular event. For planetary defense researchers, it's an invaluable opportunity to study an asteroid during a close approach. For a while after its discovery in 2004, there was significant concern that Apophis might hit us on a later pass, particularly in 2036 or 2068. The calculations showed a small but non-zero probability. This sparked serious discussions about deflection missions, about what we would do if the odds shifted unfavorably. Further observations refined the orbit, ruled out those impact possibilities. We know with certainty now that Apophis poses no threat for at least a century. But it's a reminder that space is not as empty as it seems. Objects do pass close. The 2029 pass will actually change Apophis's orbit slightly. Earth's gravity will tug on it, alter its path, affecting where it goes afterward. The difference between a miss and a hit can be surprisingly small in cosmic terms. In 2004, asteroid 2004 FH passed just 43,000 kilometers from Earth, about 1/10 the distance to the Moon. It was only about 30 meters across, but that's still large enough to cause significant damage if it hit, potentially larger than Chelyabinsk. We didn't detect it until it was already close, only a few days before closest approach. We found it, calculated it would miss, and watched it pass. But if the trajectory had been slightly different, we would have had almost no warning time. In 1989, asteroid 4581 Asclepius passed about 700,000 kilometers from Earth, roughly twice the distance to the Moon. That might seem like a comfortable margin, and it is. But here's the striking thing. If it had arrived just 6 hours earlier or later in its orbit, if its position had been shifted by a mere fraction of its orbital path, it would have struck Earth. 6 hours of difference in timing, determined by gravitational interactions that occurred millions of years in the past. The difference between a harmless pass and a catastrophic impact. That asteroid was about 300 meters across, not extinction level, but certainly civilization disrupting if it had hit a populated region, and we didn't discover it until after it had already passed. We found it in images taken days after closest approach. It came and went, and we only noticed it was there after it was gone. These near misses are more common than most people realize. Every year, several asteroids pass within the Moon's orbit. Most are small, tens of meters across, but occasionally larger ones pass close, and we don't always spot them far in advance. We're getting better, but we're not perfect. This is why detection programs like ATLAS, Pan-STARRS, and the upcoming Vera Rubin Observatory are so important. The more sky we survey, the more frequently we look, the better our instruments become, the more objects we find, and the more warning we have if one is heading our way. There's also the sobering reality that Earth has probably been struck by many more objects than we have direct evidence for. Impacts on the ocean leave no permanent crater. Water fills in immediately, and seafloor spreading eventually erases any trace. Impacts on ice sheets might leave temporary marks but would be erased as the ice flows and eventually melts. Small impacts might create craters that erode quickly or are obscured by vegetation within years or decades. The craters we've found, the ones we can study, are probably just a fraction of the total impacts Earth has experienced over its 4.6 billion year history. We're looking at the largest ones, the most recent ones, the ones in locations where preservation is favourable. The complete impact history is certainly much more extensive, and this history continues actively. Earth is struck by small meteorites constantly. Dust-sized particles burn up in the atmosphere all the time. That's what we see as meteors, shooting stars, dozens per hour on a typical night. Larger fragments, pebble-sized or boulder-sized, reach the ground regularly. Scientists collect meteorites from Antarctica, where they're preserved on the ice and easy to spot against the white background. Thousands of meteorites representing thousands of small impacts over thousands of years, teaching us about the composition of asteroids and the early solar system. Most are harmless. A fist-sized rock landing in a field or ocean doesn't hurt anyone, but occasionally they're larger, and very occasionally they land where people are. In 1954, a grapefruit-sized meteorite crashed through the roof of a house in Alabama and struck a woman named Ann Hodges, who was napping on her couch. She survived with severe bruising but no permanent injury. It's the only confirmed case of a human being directly struck by a meteorite in recorded history, but it's a reminder that even small impacts can be personal, can affect individuals, not just abstract populations. The statistical reality is that impacts occur on a spectrum, small ones constantly, medium-sized ones occasionally, large ones rarely. The larger the impact, The less frequently it occurs, but the more devastating the consequences when it does. Tunguska scale events, 50-meter objects, probably occur every few centuries on average. Most happen over oceans or unpopulated areas, simply because most of Earth's surface is ocean or wilderness. We notice and remember the ones that happen near civilization. Chelyabinsk scale events, 20-meter objects, probably occur every few decades. Again, most go unnoticed because they occur over empty regions or explode at high altitude where they don't cause ground damage. Chicxulub scale events, 10-kilometer objects, occur every 100 million years or so based on crater records and statistical models of asteroid populations. Rare enough that human civilization, barely 10,000 years old, hasn't experienced one. Common enough that life on Earth has been reshaped by them multiple times. And somewhere in between we have the 440-meter to several kilometer range. The range where impacts are devastating but not necessarily extinction level, where they reshape regions or civilizations but not necessarily all life. These probably occur every few tens of thousands to few million years, depending on size. Rare on human timescales, inevitable on geological timescales. The question isn't whether another large impact will occur. The question is when, and whether we'll be ready when it does. This is actually grounds for cautious optimism in a strange way. For the first time in Earth's 4.6 billion year history, there's a species capable of preventing impacts. Dinosaurs couldn't build telescopes or launch spacecraft. They couldn't detect an incoming asteroid or deflect it. They were subject to cosmic chance, to luck, to forces beyond their comprehension or control. We're different. We can watch the sky systematically. We can calculate trajectories precisely. We can, in principle, prevent impacts if we have enough warning. We're not helpless in the face of cosmic forces. We've moved from passive victims to active participants in our planetary defense. But we're also not invulnerable. Our capabilities are limited. Our detection systems have gaps. Our deflection technologies are still developing, still being tested, still being improved. We're in a transition period, no longer helpless, not yet fully capable, and that makes preparation crucial, makes the investments in planetary defense both urgent and worthwhile. Every near miss teaches us something. Every impact, even small ones, provides valuable data. We study the Chelyabinsk meteor fragments to understand composition and structure. We model the Tunguska explosion to understand airburst dynamics. We examine ancient craters to understand long-term effects and recovery patterns. This knowledge informs our planning. It helps us understand what we're preparing for. It helps us appreciate both the risks we face and our growing capabilities to address them. And it helps us appreciate 3I Atlas passing safely by, because we've seen what impacts can do in our lifetimes and in the geological record. We have the scars, the historical records, the near misses that remind us this is real. Space is not empty. Objects cross our path regularly. Usually they miss, but not always. And the difference between usually and always is worth preparing for. The history of impacts on Earth is a history of chance and consequence, of objects arriving at the right place and time, or the wrong place and time, depending on perspective, of survival and extinction, of catastrophe and recovery, of the universe's indifference and life's resilience. We're writing the next chapter of that history, and for the first time we have some meaningful influence over how it turns out. So let's talk about what we're actually doing to protect ourselves. Because for all the talk of cosmic threats and catastrophic scenarios, we're not sitting idle. We're building systems, developing technologies, learning to work together internationally, and genuinely making progress in defending our planet. Planetary defense is a relatively new field, emerging really only in the last few decades as we've come to understand the impact threat more clearly and develop the technological capability to do something about it. But it's advancing rapidly, and the progress we've made is genuinely encouraging. Let's start with detection, because you can't defend against what you can't see, and finding asteroids is the foundation of everything else. The first challenge of planetary defense is finding the objects that might threaten us. This is harder than it might initially sound. Space is vast beyond comprehension. Asteroids are small. Even a kilometre-wide object is tiny on cosmic scales. And they're dark, made of rock and sometimes metal, absorbing most of the sunlight that hits them. They don't emit their own light. They only reflect sunlight and often not very much of it. Finding them requires systematically searching the sky night after night, comparing images to detect anything that moves against the background of fixed stars. It's painstaking work requiring patience, precision, and increasingly sophisticated software. Several programs are doing exactly this, and they're remarkably successful. The ATLAS system, Asteroid Terrestrial Impact Last Alert System, is a network of telescopes specifically designed to find potentially hazardous objects. 4 telescopes currently spread across Hawaii, Chile, and South Africa, giving nearly continuous coverage as Earth rotates. It's the same system that discovered 3I Atlas, proving its effectiveness at finding unusual objects. Atlas scans the entire visible sky every few nights, taking images, comparing them to previous images, flagging anything that has moved. The software processes hundreds of thousands of images automatically, looking for the subtle motion that indicates an asteroid or comet. It's found thousands of near-Earth objects since it began operations. PanSTARRS, the Panoramic Survey Telescope and Rapid Response System in Hawaii, is another major contributor. It uses a telescope with an enormous field of view, about 3 degrees across, which is 6 times the diameter of the full moon, to survey large areas of sky quickly. It's discovered thousands of asteroids, including many near-Earth objects, and it's particularly good at finding distant objects in the outer solar system. The Catalina Sky Survey in Arizona has been operating since the 1990s, making it one of the oldest ongoing systematic searches. It uses multiple telescopes of different sizes to scan different parts of the sky at different depths. It's found thousands of near-Earth asteroids over the decades, including many potentially hazardous ones that required follow-up observations to confirm they weren't threats. Together, these programs and others like them around the world have catalogued about 90% of near-Earth asteroids larger than 1 kilometre. That's a remarkable achievement when you consider that we started essentially from zero just a few decades ago. We now know where most of the civilization-threatening asteroids are. We can calculate their orbits decades, sometimes centuries into the future, and none of them currently threaten us. Not in the foreseeable future. We've checked, and we keep checking. For smaller objects, hundreds of meters across, the kind that could devastate a region or cause the smaller 3I Atlas scenario we explored, the catalogue is less complete. We've probably found about 40% of asteroids in the 140-meter size range. That's significant progress, but still leaves gaps. We're finding them at a rate of hundreds per year, gradually filling in the catalogue, but it will take time to achieve the same completeness we have for larger objects. And for Chelyabinsk-sized objects, 20 meters or so, we've probably only found a tiny fraction of what's out there. There are simply too many, they're too small, too faint, and they don't reflect enough light to be easily detected. These we probably won't catalogue completely. Instead, we rely on surveys like ATLAS, that can potentially detect them in the final days or hours before impact, giving at least some warning. The next generation of surveys will help dramatically. The Vera Rubin Observatory in Chile, currently conducting the legacy survey of space and time, will revolutionize our detection capabilities when fully operational. Its telescope has a huge mirror, 8.4 meters across, and the largest digital camera ever built for astronomy, with 3.2 billion pixels. It will scan the entire visible sky every few nights, detecting objects much fainter than current surveys can see. When Rubin is fully operational, we expect to double the number of known near-Earth asteroids within its first year. It will find smaller, more distant objects. It will detect more comets from the outer solar system, and it will find more interstellar visitors like 3I Atlas, giving us better statistics on how common these objects are. But detection has fundamental limitations that are worth understanding. Telescopes can only see what's above the horizon when it's dark. They can't observe during daylight, or when the moon is bright. The sky is too bright, overwhelms the faint light from asteroids. They can't see objects approaching from the direction of the sun. That's essentially a blind spot, which is exactly how Chelyabinsk surprised us. It came from the sun's direction, and we literally couldn't see it. Some solutions are being developed. Space-based infrared telescopes would solve many of these problems elegantly. In space, there's no daylight, no weather, no atmosphere to look through, and in infrared wavelengths, asteroids glow from their own heat. They absorb sunlight and re-radiate it as infrared, making them much easier to detect. NASA has proposed several space-based survey missions, including NEO Surveyor, that would dramatically improve our ability to find threatening objects, particularly those in orbits that keep them between Earth and the Sun, where ground-based telescopes struggle. But detection is only the first step. Once you find a threatening object, once you calculate that it's heading for Earth, you need to do something about it. And this is where the field gets both more challenging and more interesting. This is where deflection comes in. And here, the DART mission represents a genuine breakthrough, a proof of concept that moved planetary defense from theory to demonstrated reality. Double Asteroid Redirection Test, DART, launched in November 2021 with a straightforward but audacious goal: deliberately crash a spacecraft into an asteroid and change its orbit measurably. The target was carefully chosen: Dimorphos, a small moon orbiting the larger asteroid Didymos. Dimorphos is about 160 meters across, and it orbits Didymos every 11.9 hours. The binary system was chosen for several reasons. It's not actually threatening Earth, so the test was safe. The orbital period is short enough to measure changes quickly, and having Dimorphos orbit Didymos provides a clear measurement of success. On September 26, 2022, after nearly a year of flight, DART struck Dimorphos at about 6 kilometers per second relative velocity. The impact was observed by telescopes around the world and by a small Italian spacecraft called LiquorCube that had separated from DART shortly before impact to watch from a safe distance. The results exceeded expectations significantly. Dimorphos's orbital period changed by about 33 minutes, from 11.92 hours down to 11.37 hours. Mission planners had predicted a change of about 7 minutes if everything went well, maybe 10 minutes if conditions were optimal. Getting 33 minutes meant something worked even better than expected. Why the extra effectiveness? Analysis suggests it's because of the debris ejected by the impact. When you hit an asteroid at 6 kilometers per second, you don't just transfer momentum from the spacecraft itself. You blast material off the surface, rock, dust, fragments, and that material flying away creates additional thrust, like a rocket exhaust, but generated by the impact. The ejector contributed significantly to the overall momentum change, perhaps 2 or 3 times as much as the spacecraft impact alone. This has important implications. It means kinetic impactors are more effective than minimal models suggested. It means the nature of the asteroid's surface matters. A loosely bound rubble pile might eject more material than solid rock. It means we need to understand asteroid composition and structure to predict deflection effectiveness accurately. This was the first time humanity deliberately changed the motion of a celestial body. It sounds almost mundane when stated that way, but pause to think about what it means. For all of human history, celestial objects have moved according to gravity and momentum, following paths determined by physics alone. Now we've proven that we can alter those paths. We can protect ourselves from impacts if we have enough warning. But DART also revealed the limitations clearly. The mission took nearly a year from launch to impact. If we'd needed to deflect Dimorphos quickly, if it had been an actual threat with months of warning, rather than a carefully planned test, we couldn't have. And while the velocity change was larger than expected, it was still modest in absolute terms, a few millimeters per second. That's enough if you have years for it to accumulate into a meaningful course change. Over 5 years, a few millimeters per second becomes tens of thousands of kilometers of deflection. But with only months of warning, it wouldn't be sufficient to turn a direct hit into a safe miss. So what other techniques might work, especially for shorter warning times or larger objects? The kinetic impactor, what DART demonstrated, is probably the simplest and currently most feasible option. Hit the asteroid hard enough, fast enough to change its velocity meaningfully. No exotic technology required, just basic orbital mechanics, precise navigation, and a spacecraft with some mass behind it. For objects detected years in advance, for asteroids in the hundreds of meters size range, this is probably our best practical option with current technology. The gravity tractor is more subtle and elegant. Park a spacecraft near the asteroid, not on it, not touching it, just hovering nearby, perhaps hovering just tens of meters away. The spacecraft's tiny gravitational pull gradually tugs on the asteroid, changing its orbit millimeter by millimeter over months or years. The advantage is precision. You can adjust continuously, fine-tune the deflection, even reverse course if needed. The disadvantage is that it's slow, very, very slow. You'd need years, possibly decades, to achieve meaningful deflection of even a modest-sized asteroid. But for objects detected far in advance, with plenty of time, it could work beautifully. And it's the gentlest option, posing no risk of fragmenting the asteroid. Nuclear deflection is the dramatic option, the one that appears in movies, and surprisingly it might actually be one of our best options for large asteroids with limited warning time. Detonate a nuclear weapon near, not on but near, the asteroid. The radiation from the nuclear explosion vaporizes part of the asteroid's surface. The expanding vapor creates thrust, pushing the asteroid off course. Models suggest this could change an asteroid's velocity by meters per second or more, far more than a kinetic impactor, potentially enough to deflect even a large object with months rather than years of warning. The challenges are significant, of course. International treaties complicate the use of nuclear weapons in space. The technical challenge of detonating a nuclear device with precise timing and positioning is substantial. And there's a risk of fragmenting the asteroid rather than deflecting it intact, potentially turning one large threat into many smaller ones. Though even that might be preferable to a single large impact, as the smaller pieces would spread out and many would miss Earth. Still, for a large asteroid with limited warning time, for something in the several hundred meter to kilometer range detected only months before impact, nuclear deflection might be our only realistic option. NASA and other agencies have studied it seriously. The technology exists. We've detonated nuclear weapons in space before during testing in the 1960s, before treaties banned such tests. Whether we could implement it in time for a real threat, whether we could navigate the political and international complexities quickly enough, remains uncertain. There's also the possibility of landing spacecraft on an asteroid and using engines, either chemical rockets or ion drives, to slowly push it off course over months or years. This is technically feasible and has been studied extensively. We've successfully landed on asteroids before, and we know how to keep engines running for extended periods. But it's slow, requires years of warning time, and is more complex than simply hitting the asteroid. For a small asteroid detected far in advance, it could work well. The key insight from all these techniques is that time matters enormously, more than almost anything else. The earlier you detect a threat, the more options you have, and the easier deflection becomes. A gentle nudge applied years in advance can turn a direct hit into a comfortable miss by hundreds of thousands of kilometers. But that same gentle nudge applied months before impact might deflect the asteroid by only hundreds of kilometers. Not enough if it was aimed directly at Earth. This brings us inevitably back to the interstellar problem, the challenge that 3I/Atlas represents. Interstellar objects moving at 60 kilometers per second, detected only when they're already in the inner solar system, sometimes only months before they'd reach Earth. These present uniquely difficult challenges that break many of our planning assumptions. Most of our planetary defense planning assumes years of warning time and solar system velocities, objects moving at 20 or 30 kilometers per second at most. 3I Atlas, if it had been on a collision course, would have shattered those assumptions. We probably couldn't have deflected it with current technology given months of warning. We'd have been reduced to preparation and evacuation, important certainly, potentially saving millions of lives, but not prevention. This is a gap in our capabilities that needs addressing as we become more aware of interstellar visitors. Potential solutions are being discussed. Pre-positioned interceptor spacecraft, vehicles already in space, already fueled, already checked out, ready to launch quickly when a threat is detected, or faster developing mission profiles that can launch and intercept within weeks rather than months, or better detection systems that spot interstellar objects farther out, when they're still beyond Jupiter's orbit, or even Saturn's orbit, giving us months of additional warning time, potentially enough to matter. These technologies don't exist yet, but they're being researched, being discussed at conferences, being included in long-term planning. And the awareness that interstellar objects present unique challenges is growing within the planetary defense community. 3I Atlas, even passing safely by, has been educational. There's also the crucial question of international cooperation. Planetary defense isn't something any one nation can do alone effectively. An asteroid threatening Earth doesn't respect borders or politics. It doesn't care about international relations. Detection networks need to be global to provide continuous coverage. Data needs to be shared freely and rapidly. Deflection missions might need to be international efforts, pooling resources and expertise. The good news is that cooperation is improving steadily. The United Nations has an Office for Outer Space Affairs that coordinates planetary defense efforts internationally. The International Asteroid Warning Network shares observational data among observatories worldwide in near real time. The Space Mission Planning Advisory Group brings together space agencies to coordinate potential deflection missions. Space agencies from multiple countries participate in planetary defense research and testing. When DART impacted Dimorphos, it wasn't just an American success. The European Space Agency's Hera mission was already being planned to visit the impact site in 2026 to study the results in detail. This kind of international collaboration, with NASA conducting the impact test and ESA conducting the follow-up scientific study, is exactly what planetary defense needs to function effectively. But challenges remain. Practical questions and political questions. Who decides whether to deflect an asteroid? If a deflection attempt might shift an asteroid's trajectory from one part of Earth toward a different region or country, who has the authority to proceed? What if deflection fails and makes things worse? These are thorny political questions without clear international frameworks yet. And then there's funding, always funding. Planetary defense is relatively inexpensive compared to many space programs. DART cost about $330 million total, less than a single flagship Mars mission. A tiny fraction of what nations spend on many other defense programs, but it requires sustained funding over decades. Detection programs need to run continuously, every night, year after year. Deflection technologies need to be developed, tested, kept ready. The risk is that when years go by without a credible threat, when no asteroid is heading our way, funding gets cut gradually, capabilities atrophy, institutional knowledge is lost. The hope is that successes like DART maintain public and political support, that the awareness of the threat combined with visible progress toward solutions keeps planetary defense adequately funded, that we don't need to experience a catastrophe to maintain our vigilance and investment. Because here's the fundamental reality: planetary defense works. We have the technology, or can develop it given time and resources, to prevent most asteroid impacts if we have adequate warning. The physics are well understood. The engineering is challenging but feasible. We've now demonstrated that deflection is possible in practice, not just theory. What we need is sustained commitment, better detection systems to find threats earlier and more completely, more research into deflection techniques, especially for challenging scenarios, international cooperation frameworks that can function under pressure, and the political will to invest in protecting Earth from a threat that might not materialize in our lifetimes or our children's lifetimes, but will eventually arrive. This is actually one of humanity's better traits, our ability to plan for long-term threats, to invest in future generations, to take on challenges that don't have immediate payoffs. Planetary defense is essentially altruistic on generational timescales. We're building systems that might not be needed for decades or centuries, but when they're needed, when that asteroid is detected on a collision course, they'll be invaluable. And there's something genuinely profound about this entire endeavour. For billions of years, life on Earth has been subject to cosmic chance. Impacts happened randomly. Species went extinct. Evolution adapted to what survived. There was no agency, no choice, no way to prevent catastrophe when it arrived from space. Now there is. We've reached a point in our technological development where we can protect not just ourselves, but the entire biosphere. We can prevent extinctions. We can ensure continuity of complex life. We're becoming, in a meaningful sense, shepherds of Earth's biology, guardians against cosmic threats. That's a responsibility worth taking seriously, and the progress over the past few decades suggests we are taking it seriously. Planetary defense has gone from science fiction to serious science, from speculation to demonstrated capability, from impossible to difficult but achievable. 3I/Atlas passing safely by was fortunate, but we're working toward a future where fortune matters less, where we have the capability to ensure safety through preparation and technology, rather than relying solely on luck and vast empty spaces. We're not there yet. Our capabilities have real limitations, but we're moving in the right direction steadily. And that's genuinely encouraging, genuinely grounds for optimism about humanity's ability to face long-term challenges. Now let's meet 3I Atlas's predecessors, the other interstellar visitors we've had the privilege of observing, because 3I Atlas isn't alone. It's part of a population of objects wandering between the stars, and each one we found has taught us something valuable about the galaxy beyond our solar system. Let's start with the first confirmed interstellar visitor, the one that changed everything, Oumuamua. On October 19, 2017, astronomers using the Pan-STARRS telescope in Hawaii detected an unusual object moving through the sky. At first, it seemed like an ordinary asteroid or comet. These are discovered regularly, and the initial reports weren't particularly exciting. But as observations accumulated over the following days, and the orbit was calculated with increasing precision, something remarkable became clear. This object wasn't bound to our sun. Its trajectory was hyperbolic, its velocity too high to be captured by solar gravity. It had come from interstellar space, passed through our solar system, and was heading back out into the cosmic dark. They named it Oumuamua, a Hawaiian word meaning roughly scout or messenger from the distant past arriving first. A fitting name for humanity's first confirmed visitor from beyond, discovered by a Hawaiian telescope looking outward toward the rest of the galaxy. Oumuamua was strange in several ways that made it memorable and sparked ongoing debates. Its shape was highly unusual, extremely elongated, perhaps 10 times longer than it was wide. Estimates suggested it might be cigar-shaped, maybe 100 to 400 meters long and only 35 to 40 meters wide, though the uncertainty was quite large because we never got close-up images. We only saw it as a point of light, inferring its shape from how its brightness varied as it tumbled through space, reflecting different amounts of sunlight depending on its orientation. The tumbling itself was odd, chaotic, complex, not the simple rotation you'd expect from a normal asteroid. It was tumbling end over end in multiple axes, suggesting it might have been ejected violently from its home system during some dramatic event, or perhaps had experienced a collision at some point in its billions-year journey through interstellar space. The colour was reddish, similar to what 3I Atlas would show years later, suggesting organic compounds that had been irradiated by cosmic rays during the long journey between stars. This wasn't surprising. Scientists had predicted that interstellar objects would show this coloration based on laboratory experiments simulating cosmic ray exposure. But then things got genuinely interesting, sparking debates that continue to this day. As Oumuamua moved away from the Sun, past Earth's orbit and heading outward, it showed a slight but measurable acceleration. Not much, just a tiny change in velocity, a few centimeters per second, but detectable with precise measurements and clearly present in the data. In comets, this kind of acceleration is completely normal and well understood. It's called the rocket effect or outgassing effect, as ice sublimates from the sun-facing side, particularly as the comet approaches the sun and heats up. The escaping gas creates thrust, acting like a tiny rocket engine. We see this in every active comet and can calculate it precisely. But Oumuamua showed no visible signs of cometary activity whatsoever. No coma, no tail, no detectable outgassing in any wavelength we observed. It looked like an asteroid, not a comet. Asteroids don't accelerate, they follow predictable gravitational paths. So what was causing the acceleration? Multiple hypotheses were proposed, each with strengths and weaknesses. Perhaps it was outgassing water or some other volatile, but too faintly to detect at that distance with our instruments. Perhaps it was a very thin, flat object, more like a pancake or disk than a cigar, and solar radiation pressure was actually pushing it, like a solar sail. Perhaps it was made of hydrogen ice, which would sublimate without leaving visible traces because hydrogen is so light and transparent. Or perhaps, and this is where things got creative and captured public imagination, it was artificial, an alien spacecraft, a probe from another civilization, using some form of propulsion we couldn't detect. This hypothesis was championed by some scientists and got enormous media attention, though most astronomers remained skeptical, noting that the simplest explanation was usually outgassing that our instruments just couldn't detect. The scientific debate continues. Papers are still being published analysing Oumuamua's trajectory and properties, but we'll never know for certain with the data we have because Oumuamua is long gone now. By the time we fully realised how unusual it was already leaving, already too far away for detailed follow-up observations. We watched it fade from view over the following months, moving back into the interstellar dark, carrying its mysteries with it, perhaps never to be observed again. The experience was frustrating scientifically but profoundly educational. We learned that interstellar objects pass through our solar system regularly. Oumuamua probably wasn't the first, just the first we noticed and confirmed. And we learned an important lesson. When we spot another one, we need to study it quickly and thoroughly, mobilize resources immediately, because the opportunity window is brief before it's gone. That opportunity came just 2 years later, and this time we were better prepared. On August 30th, 2019, amateur astronomer Gennady Borisov, using a 0.65-meter telescope he built himself at the Margot Observatory in Crimea, discovered what he initially thought was a faint comet. And it was indeed a comet with a visible coma and developing tail. Classic cometary features. But as professional astronomers followed up and calculated its orbit, they made an exciting discovery. Like Oumuamua, its orbit was hyperbolic. Another interstellar visitor had arrived. They named it 2I/Borisov, with the 2I indicating the second confirmed interstellar object. And this time, the astronomical community was ready. This time, we had time. Borisov was discovered much earlier in its approach than Oumuamua had been, giving us months to observe it as it approached the Sun, passed through the inner solar system, and departed. Telescopes around the world turned toward it immediately. The Hubble Space Telescope observed it multiple times, capturing detailed images. The Very Large Telescope in Chile studied it with powerful spectrographs. Radio telescopes searched for unusual emissions. We threw everything we had at it, gathering a wealth of data. Borisov was smaller than 3I Atlas would prove to be. Estimates suggested a nucleus perhaps 400 to 500 meters across. Though, as always with comets, the uncertainty was significant because the nucleus was hidden within the coma. It was clearly and unambiguously a comet, actively outgassing as it approached the Sun, developing a tail that eventually stretched for thousands of kilometers behind it, showing all the classic cometary behaviors. The composition was fascinating and scientifically valuable. Spectroscopic observations showed water vapor, of course. That's the primary component of most comets. But also carbon monoxide in unusually high concentrations relative to water. The ratio of carbon monoxide to water was higher than in most solar system comets, though not completely unprecedented. Some solar system comets from the outer reaches also show elevated CO ratios. This suggested different formation conditions. Perhaps Borisov formed farther from its parent star, in colder regions where carbon monoxide doesn't sublimate away as easily during the early solar system formation phase. The colour was reddish, like Oumuamua, like 3I Atlas would be. This seems to be a consistent, universal feature of interstellar objects, that organic reddish tint from billions of years of cosmic ray exposure. It's becoming a signature, a way to potentially identify interstellar objects even before we calculate their orbits precisely. But in most other ways, Borisov looked remarkably like a comet from our own solar system. Its behaviour was normal, predictable, following all the patterns we've observed in solar system comets. Its composition, while slightly unusual in some ratios, was within the range we see in our own comets. This was actually quite reassuring scientifically. It suggested that planet formation produces fundamentally similar objects wherever it occurs in the galaxy. That comets from other star systems aren't alien or exotic, just variations on a universal theme, that the chemistry and physics of planet formation are consistent across different stellar environments. Borisov passed through our solar system, rounded the Sun at perihelion, and headed back out into interstellar space. Unlike Oumuamua, with its mysteries and debates, we understood Borisov. No unusual accelerations, no speculation about alien probes, no unexplained behaviours. Just a comet from another star system, visiting briefly, behaving exactly as cometary physics predicts. Almost disappointingly normal, if you can call an interstellar visitor disappointing. And then came 3I Atlas in 2025, the subject of our exploration tonight. Compared to its predecessors, 3I Atlas was spectacular in every way, potentially larger than Borisov, possibly much larger depending on which size estimate proves correct, ranging from 440 metres to 5.6 kilometres. More active than either predecessor, developing a more prominent coma and tail that made it easier to study, brighter, visible for longer, approaching more favourably for observations from Earth's perspective. We detected it earlier than Oumuamua but had more time to study it systematically than either predecessor, allowing for comprehensive observations. Multiple observatories tracked it throughout its entire passage through the inner solar system. The Hubble Space Telescope devoted significant observing time to it. The James Webb Space Telescope, with its powerful infrared capabilities, studied it extensively. Ground-based observatories around the world coordinated observations. We gathered spectroscopic data across multiple wavelengths, photometric measurements tracking its brightness variations, everything we could possibly measure. The composition showed interesting and subtle variations from Borisov. Different ratios of volatiles, more water relative to carbon monoxide, slightly different abundances of complex organics. The dust-to-gas ratio appeared different, not dramatically different, not incomprehensibly alien, but measurably distinct. This tells us something profound. Different star systems produce comets with subtle but detectable chemical differences, chemical fingerprints of their stellar origins, signatures of the specific conditions in those distant stellar nebulae billions of years ago. So what have these three visitors, Oumuamua, Borisov and 3I Atlas, taught us collectively about the galaxy and our place in it? First, and perhaps most importantly, they've shown us that interstellar objects are common, not rare curiosities. 3 confirmed detections in 8 years, combined with our understanding of how incomplete our surveys are, suggests that interstellar objects pass through the inner solar system regularly, probably 1 per year or more on average, with most too small or faint to detect with current technology, or approaching from angles that make them difficult to observe. Second, they've demonstrated that interstellar objects are diverse, not uniform. Oumuamua was rocky, or at least behaved like a rocky object, showing no obvious cometary activity. Borisov and 3I Atlas were clearly comets, actively outgassing. This diversity suggests that planetary systems eject both asteroids and comets into interstellar space through different mechanisms: gravitational interactions with giant planets, stellar encounters, perhaps other processes we haven't fully understood yet. Third, they've shown us that these objects are ancient time capsules, billions of years old typically, formed around young stars when those systems were first taking shape, ejected early in those systems' histories through gravitational interactions, and drifting through the galaxy ever since. They're literally time capsules, carrying chemistry and structure from the era when their parent stars were newly formed, preserving information about stellar nebulae that dissipated billions of years ago. Fourth, they've revealed that interstellar objects are chemically distinct but recognizable. Each shows variations that mark it as foreign, as formed under different stellar conditions, with different element abundances and formation temperatures, but none are so strange as to be incomprehensible. The fundamental chemistry of planet formation appears to be universal: hydrogen, carbon, oxygen, nitrogen, the same periodic table, the same physical laws, just with local variations depending on stellar composition and formation conditions. And fifth, they've made it clear that we need better detection capabilities urgently. We've probably missed many more interstellar objects than we've found, smaller ones that don't reflect enough light, fainter ones that our surveys aren't sensitive enough to detect, ones that approached from unfavourable angles or during periods when we weren't observing. As our telescopes improve, as our search programs expand in coverage and sensitivity, we'll find more. Many more. And each one will teach us something valuable about other star systems, about the mechanisms that eject material into interstellar space, about the galactic environment we live in. There's something genuinely profound about these visitors when you pause to think about it. Each one is a physical messenger from another star, from a place light years away that we'll probably never visit with our current technology, or possibly ever. They bring us samples, literally physical samples of matter from other stellar environments, material that formed light years away, under different conditions in different stellar nebulae, shaped by different planetary formation processes. When we study 3I Atlas's spectrum through our telescopes, we're analysing chemistry from another star system. When we measure isotope ratios, we're learning about the composition of a stellar cloud that existed billions of years ago in some distant part of the galaxy. When we watch how it outgasses and responds to solar heating, we're learning about how comets form in other planetary systems. These objects are bridges between stars, physical connections between stellar systems that are otherwise separated by vast, essentially impassable distances with current technology. The galaxy, we're learning, is more interconnected than it might initially appear. Stars don't just exist in isolation, separate island systems. They exchange material, albeit slowly and randomly over millions of years. Planetary systems form, eject material through various mechanisms, and that material wanders through the interstellar medium until eventually, sometimes billions of years later, it encounters another star by pure chance. Sometimes it gets captured if the conditions are right. Sometimes it impacts planets, potentially delivering organic compounds or even water. Sometimes, very rarely, someone happens to be watching with telescopes when it passes through. We're learning through direct observation that our solar system isn't sealed off from the rest of the galaxy. We're part of a larger ecosystem, if you can call it that. Material flows through, carries information, connects us to stellar processes and planetary systems light years away. And here's something worth considering, a speculation that scientists debate. Could interstellar objects have contributed to the origin of life on Earth? This is the hypothesis of panspermia, that life itself, or at least its building blocks and chemical precursors, might travel between star systems on objects like these. Complete organisms travelling between stars probably couldn't survive. It's too harsh a journey. Cosmic rays, intense radiation, temperature extremes, the vacuum of space, billions of years of exposure. Most complex molecules like DNA or proteins would be destroyed, broken down into simpler components. But simpler building blocks of life might survive the journey. Amino acids, simple sugars, nucleobases, the fundamental components that life uses. We find these organic compounds in meteorites from our own solar system regularly. They survive impact, can be recovered intact. If they can survive within our solar system for billions of years, perhaps they can survive interstellar journeys as well, protected deep within the interior of comets and asteroids. It's highly speculative, and most scientists think life arose independently on Earth from simple chemistry and favourable conditions. But the possibility that Earth's prebiotic chemistry was enriched by interstellar contributions, that some of the organic building blocks arrived from beyond our solar system, delivered by objects like Oumuamua or Borisov, that's at least plausible enough to be worth considering and studying. Either way, regardless of life's origins, these objects connect us to the galaxy in ways that are both physical and conceptual. They remind us that we're not isolated in space, that matter moves between stars on long timescales, that the galaxy is dynamic, active, full of ongoing processes of exchange and interaction, even if those processes unfold over millions of years. The 3 interstellar visitors we've confirmed so far, Oumuamua, Borisov, 3I Atlas, are almost certainly just the beginning of a much longer catalogue. As our detection capabilities improve steadily, as telescopes become more sensitive and surveys more comprehensive, we'll find more. Many more. We'll build up robust statistics on their frequency, their size distribution, their compositions. We'll learn which types of star systems eject the most material into interstellar space and why. We'll understand the galactic population of wanderers more completely, map out their properties and origins. Perhaps someday, if we're fortunate and ambitious, we'll even send a mission to intercept one. If we detect an interstellar object early enough, while it's still beyond Jupiter's orbit with years before closest approach, if we have adequate warning time and sufficient funding, we might be able to launch a spacecraft to match velocities with it, to study it up close with instruments, to land on its surface, to sample it directly, and analyze material from another star system in detail. Imagine the scientific return from directly analyzing material from another stellar environment. That's still science fiction for now, admittedly. We don't have spacecraft capable of achieving the velocities needed to catch up with objects moving at 60 kilometers per second through the inner solar system. The fastest spacecraft we've built, New Horizons, the Parker Solar Probe, reach impressive speeds, but still not enough for this application. But perhaps in the future, with better propulsion technologies, with more warning time from improved detection, it becomes possible. It's a worthy long-term goal. For now, we watch from Earth and from Earth orbit. We study from hundreds of millions of kilometers away using reflected sunlight and emitted thermal radiation. We learn what we can from the photons they send us, from their trajectories through our solar system, from the spectra that reveal their composition. And we appreciate them for what they truly are, visitors from the vast dark between stars, brief glimpses into planetary environments we may never see directly, physical evidence that the galaxy is full of planetary systems undergoing similar processes to our own, connected across light years by these wandering messengers carrying information and matter between the stars. 3. Atlas, like its predecessors, came and went, arrived from the interstellar dark, passed through our neighbourhood for a few brief months, departed back into the cosmic night. But it left us with knowledge, with invaluable data, with a deeper understanding of the galaxy we inhabit and our connection to the larger cosmos. Let's step back now and consider the bigger picture. What does all of this, the scenarios we've explored, the physics we've examined, the possibilities we've imagined, teach us about Earth's place in the cosmos, about our vulnerability, about our remarkable fortune? Because that's really what this entire exploration has been about. Not fear, but perspective. Not panic, but understanding. Not despair, but awareness. Consider the odds we've been discussing throughout this journey. An interstellar object passes through the inner solar system roughly once per year on average. Most are small, tens of meters, maybe 100 meters across. Most pass at safe distances, nowhere near Earth's orbital path. The solar system is vast, hundreds of millions of kilometers across, even just in the inner regions. Earth is tiny by comparison, about 12,000 kilometers in diameter. For an interstellar object to actually hit us requires a very specific trajectory, a precise intersection of paths through three-dimensional space at exactly the right moment. The odds for any particular object are extraordinarily low, astronomically low, if you'll forgive the pun. But over long enough timescales, over millions and billions of years, rare events become inevitable. This is simply the nature of probability. Given enough opportunities, enough rolls of the dice, even unlikely things eventually happen. It's not a question of if, but when. Earth has been struck by large objects before. Chicxulub proves it definitively. The crater record scattered across the planet proves it. Geological evidence preserved in rock layers proves it. Impacts are not theoretical abstractions or Hollywood inventions. They're part of Earth's history, woven into the geological record, visible to anyone who knows how to look and interpret what they're seeing. And they'll happen again. Not tomorrow, probably not in our lifetimes, possibly not for thousands or tens of thousands of years. But eventually, given enough time, another large impact will occur. The question isn't if, but when. And crucially, whether we'll be ready when it does. And here's what's genuinely remarkable when you think about it. For the first time in Earth's 4.6 billion year history, there's a species living on the surface that can see these threats coming and potentially do something about them. Think about that for a moment. Really consider what it means. For billions of years, impacts just happened. No warning, no preparation, no prevention possible. Dinosaurs couldn't build telescopes or satellites. They couldn't calculate orbital mechanics or launch spacecraft. They were brilliant animals in their own right, supremely successful for 165 million years, far longer than humans have existed, or likely will exist. But they were subject to cosmic chance, to forces beyond their comprehension or control. We're different. We can watch the sky systematically with increasingly sophisticated instruments. We can predict trajectories years or decades in advance with remarkable precision. We've demonstrated through the DART mission that we can actually deflect asteroids, change their paths, prevent impacts. We're not helpless. We've moved from passive victims to active participants in our planetary defense. But we're also not invulnerable, and this is important to acknowledge honestly. Our capabilities have real limits. We can defend against threats we see coming with years of warning time and adequate resources. But months? That's challenging with current technology. Weeks? Probably impossible for large objects. And interstellar objects, arriving fast from unpredictable directions with limited warning time, represent a genuine gap in our defences. A challenge we're only beginning to understand and address. This is actually okay to acknowledge. Recognizing limitations isn't defeatism or pessimism, it's honest assessment. It helps us focus resources appropriately, develop better detection systems, research faster deflection methods. You can't improve what you don't measure or acknowledge. The goal isn't perfect safety. That's impossible. There's always some irreducible level of risk in existing on a planet that orbits through space. The goal is reasonable preparedness, reducing risk to acceptable levels, maintaining vigilance without becoming obsessive or paralyzed by fear. And context matters enormously here. Let's put the impact risk in proper perspective alongside other risks we face as individuals and as a civilization. The odds of a Chicxulub-scale impact occurring in any given year are roughly 1 in 100 million. That's incredibly rare. You personally are far more likely to die in a car accident, from disease, from countless other mundane causes that we accept as part of life. On an individual level, on the scale of a human lifetime, impact risk is essentially negligible. You shouldn't worry about it in your daily life any more than you worry about being struck by lightning. But on a civilizational level, the calculation is different. A Chicxulub-scale impact doesn't kill one person. It potentially ends civilization, resets technological development, causes a mass extinction. So even though the annual probability is tiny, the consequences are so enormous that investing in prevention is worthwhile. It's basic risk management. Probability times consequence equals risk. This is why we invest in planetary defense despite the low probability. Not because impacts are likely in our lifetimes or even in many human lifetimes, but because the cost of prevention is modest compared to the consequence of failure. Think of it as insurance. You pay car insurance premiums your whole life and hopefully never need a major payout. But you pay them anyway because the protection is worth it, because the alternative, being unable to cover the costs of a serious accident, is unacceptable. Planetary defense is civilization-scale insurance. We invest modestly now, a few $100 million per year globally, less than the cost of a single military fighter jet, to protect against a threat that might not materialize for centuries, but would be catastrophic beyond measure if it did. That's not paranoia. That's rational risk management, and it's working. We've catalogued most large near-Earth asteroids. We've demonstrated that deflection is feasible. We're building better detection systems steadily. The trajectory is positive. Now let's think specifically about what 3 iAtlas has taught us through this exploration, both the real object and our thought experiments about it. It reminded us viscerally that we're not isolated in the galaxy, that objects from other star systems pass through ours regularly, that the space between stars, while vast and mostly empty, isn't completely empty. It's full of wandering objects, each carrying physical samples and chemical information from distant stellar environments. It showed us that interstellar objects are scientifically valuable and diverse. Each one teaches us about planet formation processes elsewhere in the galaxy, about stellar chemistry and composition, about the mechanisms that eject material into interstellar space. It highlighted specific gaps in our planetary defense capabilities, the extreme speed of interstellar objects, the limited warning time from detection to potential impact. These are challenges distinct from solar system threats that we need to address as we become more aware of this category of potential impact. And it demonstrated something philosophically important. The universe operates on vast scales of time and space that dwarf human experience. Events that seem impossibly unlikely on human timescales become statistically inevitable on geological timescales. This perspective is genuinely valuable. It's humbling in the right way, not crushing or despairing, but grounding. It reminds us that we're part of something much larger and longer lasting than ourselves or our civilizations. Earth has been here for 4.6 billion years. It will likely be here for billions more, until the sun eventually expands into a red giant and consumes it in perhaps 5 billion years. We humans are a brief moment in that immense history, a few 100,000 years of our species existing, maybe a few million years total if we're fortunate and adaptable, a blink compared to billions of years of planetary existence. But we're a special moment in Earth's history nonetheless. The first moment when the planet's biosphere became self-aware, became capable of understanding its place in the cosmos, became able to defend itself consciously from cosmic threats. That's genuinely remarkable when you stop to think about it. For billions of years, life on Earth was subject to forces beyond its control or comprehension. Now there's a species that can look up at the night sky, understand what those points of light represent, calculate orbital mechanics, and take action to prevent catastrophes. This capability comes with responsibility. We're not just responsible for ourselves and our own survival, but for preserving the biosphere as a whole. We've reached a point where we can potentially prevent mass extinctions, not just our own extinction, but the extinction of countless other species as well. If we detect an incoming asteroid decades in advance and successfully deflect it, we're not just saving human civilization and our accumulated knowledge. We're saving countless species that would otherwise go extinct, preserving ecosystems that took millions of years to evolve, protecting genetic diversity that represents billions of years of evolutionary history. That's worth the investment of resources and attention, worth the vigilance, worth taking seriously as a civilizational priority. But let's also maintain reasonable perspective about our actual situation right now, today. We're safe. No asteroid currently threatens us. No comet is on a collision course. The Near-Earth Object Catalogue, representing decades of careful observation and calculation, shows decades more of safe passage ahead. 3i Atlas passed safely by, just as predicted. It gave us knowledge and perspective, not catastrophe. It reminded us of possibilities without actually threatening us. It was a gift of scientific data and cosmic awareness, not a close call we barely survived. This is actually the usual state of affairs, the normal condition. Most of the time, space is empty and safe for us. Objects pass by harmlessly at comfortable distances. The vast distances between celestial bodies protect us. The emptiness of space is a feature, not a bug. It's what makes cosmic collisions so rare despite the countless objects orbiting through the solar system. We live in a relatively quiet epoch of the solar system's history, the early bombardment period, billions of years ago when impacts were frequent and intense, when the planets were still forming and clearing their orbital zones, is long over. The solar system has largely cleared itself of debris through billions of years of collisions and gravitational interactions. What remains is manageable with modern technology and reasonable vigilance. Could an impact happen tomorrow? Technically, yes, it's physically possible. Probabilistically, it's extraordinarily unlikely. We've looked systematically. We've searched the sky. We've found the dangerous objects and calculated their orbits, and none threatens us in the foreseeable future. Could an object we haven't detected strike us? Yes, that's possible, especially smaller objects in the tens of meters range. Chelyabinsk in 2013 taught us that lesson clearly, but small impacts, while potentially damaging locally and dangerous to anyone nearby, aren't existential threats to civilization or the biosphere. The large objects, the civilization-threatening ones, the extinction-scale impactors, we've mostly found them, and we keep looking systematically for the rest. The catalogue improves every year as surveys continue. This should be reassuring rather than frightening. We're doing the necessary work, we're watching, we're prepared adequately, if not perfectly. And there's something genuinely beautiful about this entire endeavour when you consider it. Planetary defence represents humanity at its best, cooperating internationally across political boundaries, thinking long-term beyond election cycles, investing in future generations will never meet, using science and technology constructively to solve problems. It's not driven primarily by profit or national advantage. It's driven by the simple recognition that we share one planet, and protecting it benefits everyone equally. An asteroid doesn't discriminate by nationality. The international cooperation in planetary defence, observatories freely sharing data, space agencies collaborating on missions, scientists working together across borders, shows what we're capable of when we recognise common threats and common interests. Perhaps that's one of the gifts of cosmic perspective. When you look at Earth from space, as astronauts have described, borders disappear. Political divisions seem artificial and temporary. We're all on this one planet together, orbiting through space, subject to the same cosmic forces. An asteroid doesn't care about ideology or politics or historical grievances. It's a problem we face collectively as a species, and we're learning to respond collectively, pooling knowledge and resources across boundaries. This gives me genuine hope, not just about planetary defence specifically, but about humanity's capacity to face other long-term challenges. Climate change, resource management, pandemic preparedness. These also require long-term thinking, international cooperation, investment in solutions that might not pay off immediately. We're capable of it. Planetary defence proves it's possible. We can cooperate, we can plan ahead, we can invest in the future. So what's the main takeaway from this entire exploration? From imagining 3i/Atlas on a collision course, from walking through the scenarios in detail, from understanding the physics and the probabilities. First, that we're vulnerable but not helpless. We face real risks from cosmic impacts. This is not fiction or exaggeration, but we have growing capability to defend ourselves effectively. Second, that vigilance matters practically. Detection systems need continued funding and support. The work isn't glamorous, scanning the sky night after night, cataloguing objects, refining orbits, but it's essential for our long-term survival. Third, that our capabilities have limits we need to acknowledge and address. Interstellar objects present unique challenges. Short warning scenarios are difficult with current technology. We should invest in closing these gaps. Fourth, that perspective is valuable both emotionally and practically. We're part of a dynamic universe. Impacts have shaped Earth's history and will continue to do so. Understanding this helps us plan appropriately without panic. And fifth, that we're fortunate in this particular moment of history. 3. I-Atlas passed safely by. The asteroids we've catalogued don't threaten us. We live in a relatively safe era with the capability to make it even safer. This isn't cause for complacency. The work continues, and must continue, but neither is it cause for anxiety or fear. The odds are substantially in our favour, and we're actively working to improve them further through better detection and proven deflection capabilities. Tonight, when you look up at the stars, you can do so with understanding and appreciation rather than fear. Those distant points of light are suns like ours, possibly surrounded by planetary systems of their own, possibly ejecting their own wanderers into the galactic dark just as our system does. Someday, billions of years from now, pieces of Earth might wander between stars too. Perhaps fragments of our cities, our artifacts, evidence of our existence, scattered to the cosmos when the sun finally expands. We'll become someone else's interstellar visitor, carrying information about our solar system to distant futures we can't imagine. But that's billions of years away. For now, for the foreseeable future measured in human lifetimes and civilizational timescales, we're safe on Earth, protected by distance, by the emptiness of space, by the vast improbability of precise cosmic collisions. And increasingly we're protected by our own vigilance, by our telescopes constantly scanning, by our calculations and predictions, by our growing ability to see threats coming years in advance and do something meaningful about them. That's the real message of 3I/Atlas and this entire exploration. Not that we're in imminent danger, but that we're aware of the possibilities. Not that we're helpless, but that we're increasingly capable. Not that we should fear the cosmos, but that we should understand it and our place within it. And with understanding comes the ability to protect ourselves and our world, to preserve not just humanity, but the entire biosphere we're part of and responsible for, to be thoughtful stewards of this remarkable planet that's been our home for hundreds of thousands of years and could remain so for a long time to come. That's a worthy goal, and we're making real, measurable progress toward it, year by year, discovery by discovery, mission by mission. So let's end this chapter where we began, with 3I/Atlas passing safely through our solar system. A visitor from beyond, here briefly, then gone. It gave us wonder and knowledge rather than destruction. It reminded us of the universe's vastness and our small but significant place within it. And it passed us by, continuing its billion-year journey through the galaxy, leaving us safe to continue our own journey through time and space on this fortunate planet. That's the story of 3I/Atlas, not a catastrophe, but a gift, not a threat realized, but a perspective gained, not something to fear, but something to learn from and appreciate. Let's return to what actually happened, to reality rather than speculation, to the gift we received rather than the catastrophe we imagined. 3I/Atlas arrived in our solar system in July 2025. Astronomers using the Atlas telescope network detected it, calculated its trajectory with increasing precision, and confirmed what made it genuinely special, an interstellar visitor, only the third we'd ever confirmed. It developed a beautiful, impressive tail as it approached the sun. Telescopes around the world studied it intensively. We learned about its composition, its outgassing behavior, its ancient chemistry from another star system. We measured its size, though uncertainties remained. We tracked its path through our neighborhood. And then it departed, faded from view as it moved back toward the outer solar system and beyond, continued on its billion-year journey through the galaxy, carrying chemistry from its birth star into the cosmic dark. It passed us safely, exactly as the calculations predicted. No course corrections needed, no deflection attempts, no emergency preparations, just careful observation and precise mathematics confirming that we were never in danger. No impact, no catastrophe, no extinction event, no regional devastation, no tsunamis, just a fascinating astronomical observation and a wealth of scientific data that researchers will be analysing for years to come. This is worth appreciating deeply. The universe gave us an extraordinary opportunity to study an interstellar object, something from beyond our solar system carrying information from stellar environments light years away, without threatening us in any way. We got all the knowledge without any of the danger. That's fortunate in the most literal and profound sense. Consider carefully what we gained from 3I/Atlas's safe passage. data about interstellar chemistry that will inform our understanding of other star systems for years. Insights into comet formation processes around stars with different compositions than our Sun. Better statistics on how common these objects are and how they behave when they enter stellar systems. Each piece of information helps us understand the galaxy we live in more completely. But we also gain something less tangible yet equally valuable: perspective. A reminder that we live in a dynamic, interconnected universe where objects wander between stars, carrying matter and information across vast distances, a sense of our connection to larger cosmic processes that span millions of years, an appreciation for both our vulnerability to these forces and our growing capability to understand and respond to them. The thought experiments we've explored together tonight weren't meant to frighten you or keep you awake with worry. They were meant to illuminate, to educate, to help us understand clearly what's possible, what's at stake, and what we're capable of as a species. By imagining the impact scenarios in detail, both the survivable regional catastrophe and the potentially extinction-level event, we can better appreciate the safety we actually have. The vast distances between objects that usually protect us, the emptiness of space that makes precise collisions so extraordinarily rare despite the countless objects orbiting through the solar system. And we can better appreciate the often invisible work being done every night to keep us safe. The astronomers scanning the sky systematically, the engineers developing and testing deflection technologies, the diplomats building frameworks for international cooperation, the scientists analysing data and refining our understanding. These aren't abstract concerns or Hollywood fantasies disconnected from reality. They're real efforts by real people addressing real risks, with increasingly real solutions. But they are also not causes for alarm or anxiety in your daily life. The odds remain substantially in our favour, overwhelmingly so. The universe is vast beyond comprehension. Earth is tiny. Most objects pass by harmlessly at comfortable distances, just as 3i Atlas did. What happened with 3i Atlas is what usually happens, what typically happens, what we should expect to keep happening. Safe passage, fascinating observation, knowledge gained without cost, no catastrophe, no close call. Just normal astronomical phenomena operating as physics predicts. This is the actual state of affairs, and it's worth acknowledging that explicitly after all the scenarios we've imagined, for all the what-ifs we've explored, for all the physics we've walked through, the reality is simpler and more reassuring. We're safe. Today, tomorrow, for the foreseeable future, as measured in human lifetimes and even many generations beyond. The sun will rise tomorrow morning just as it always has, just as it has for billions of years. No comet visible in the sky, no impact threatening, no emergency broadcasts. Just another ordinary day on stable Earth, orbiting our stable, reliable sun in our remarkably quiet corner of the galaxy. This stability, this predictability, this safety, these are precious. We should appreciate them without taking them for granted. Understand the forces that could potentially disrupt them without being paralyzed by fear of those forces. Know the risks without obsessing over them. That's the balance we're seeking. Awareness without anxiety, preparedness without paranoia, understanding without despair, knowledge without fear. And 3. Atlas has helped us find that balance beautifully. It reminded us that cosmic events can affect Earth, that we're not isolated from the universe. It showed us that interstellar objects pass through our solar system regularly, connecting us to the broader galaxy. But it also demonstrated clearly that most pass safely at comfortable distances, that we can detect them effectively, that we can study them scientifically without being threatened by them. The miss is the gift, the safe passage, the knowledge without catastrophe, the lesson without loss. This is what we should celebrate and appreciate. Think about everything we've learned through this exploration together, about impact physics and the staggering energies involved, about how velocity matters more than mass, about the difference between regional catastrophes and global extinction events, about human resilience and theoretical survival strategies, about current planetary defense capabilities and the international cooperation that makes them possible. All of this understanding, all this knowledge, came from asking, what if? From imagining possibilities carefully, from following the physics to its logical conclusions, from thinking through scenarios honestly without flinching from difficult truths. This is how we prepare effectively, not by ignoring risks or minimizing them, not by catastrophizing or panicking, but by understanding clearly, planning rationally, and acting appropriately, by facing possibilities squarely while maintaining perspective about probabilities. We understand now that impacts can happen. We've seen the evidence preserved in craters scattered across Earth. We've examined geological records of past extinctions. We've experienced small impacts in living memory. Tunguska, Chelyabinsk. We know large ones are possible, even if rare on human timescales. But we also understand something equally important. We can defend ourselves. Detection systems work and keep improving. Deflection is feasible and has been demonstrated. International cooperation is possible and growing. The future isn't predetermined by cosmic chance alone. We have agency, capability, choice in how we respond to threats. This is genuinely empowering rather than frightening when you frame it properly. We're not helpless victims passively awaiting cosmic forces beyond our control. We're active participants in our own planetary defense with growing capability and improving tools. And the work continues steadily. New telescopes coming online that will dramatically improve detection, better algorithms processing more data faster, deflection technologies being refined and tested, international frameworks being established and strengthened. Each year, each mission, each discovery makes us incrementally safer. 3. IATLAS contributed meaningfully to this progress. It gave us invaluable data about interstellar objects that will inform future planning and threat assessment. It reminded both the public and policymakers that these objects exist and pass through regularly. It kept planetary defense visible and relevant in news cycles and budget discussions. It sparked conversations about readiness and capability. That's valuable precisely because it didn't hit us. The awareness it generated, the attention it focused on planetary defense, the renewed commitment to vigilance and preparation, these benefits came without any cost in lives or infrastructure damage or economic disruption. That's the ideal outcome, the best possible scenario, learning and preparing without experiencing catastrophe, building capability before we desperately need it, rather than in panicked response to tragedy, preventing problems rather than recovering from disasters. It's like fire drills in schools and offices. You practice evacuating not because the building is currently burning, not because flames are threatening anyone, but so you're prepared and practiced if fire ever does break out. The drill itself is the success. It means you're preparing systematically without having experienced the emergency. 3 IATLAS was a cosmic fire drill on a planetary scale. It reminded us of the risk clearly. It tested our detection capabilities in real conditions. It sparked useful discussions about response strategies and gaps in our defences, all without actually threatening us, without requiring any emergency response beyond increased observation time. We should be genuinely grateful for that, for the warning without the impact, for the lesson without the catastrophe, for the perspective without the trauma, for the gift of the miss, And we should take that gift seriously by continuing and expanding the work, funding detection programs adequately and consistently, supporting deflection research and development, maintaining and strengthening international cooperation, planning thoughtfully for long-term threats even when they seem distant or unlikely in our lifetimes. Because someday, perhaps centuries from now, perhaps longer, but eventually, another object will arrive on a trajectory that threatens us. Maybe an asteroid from within our solar system whose orbit we miscalculated. Maybe another interstellar visitor moving too fast to deflect easily. And when that day comes, whenever it comes, we want to be ready. We want our descendants to be ready. We want to have the telescopes that detected the threat years in advance, the computational power that predicted the impact point precisely, the tested deflection capabilities to prevent the collision, the established international frameworks to coordinate global response quickly and effectively. We want future generations to experience what we experienced with 3I Atlas. Safety maintained despite the theoretical threat, knowledge gained without catastrophe, the gift of the miss made possible by preparation and capability built up over decades of sustained effort. That's worth working toward consistently, worth investing resources in, worth maintaining vigilance for across changes in governments and public attention, worth taking seriously as a civilizational priority. But for now, tonight, as we close this exploration, we can rest easy. 3I Atlas is gone, millions of kilometers away and receding further with each passing second, continuing its journey through the galaxy. Earth remains safe. The sky remains peaceful. The cosmic visitor came, gave us data and perspective, and went, leaving us with knowledge, but not danger. That's something to appreciate genuinely as you settle into sleep tonight. We explored catastrophic scenarios together, walked through extinction possibilities in detail, imagined civilizations ending and species going extinct, but these remained imaginary, confined to thought experiments. The reality is much simpler and more comforting. Safety, stability, continued existence on our protected planet. Tomorrow, you'll wake up to the same world you've always known, the same sun rising in the east, the same earth solid beneath your feet. The cosmic visitor will be millions of kilometers farther away, fading into the interstellar dark, while you continue your life here, on this fortunate planet. That continuity is the real story of 3I Atlas. Not the catastrophe that didn't happen, but the safety that did. Not the impact we imagined together, but the stability we actually experience. Not the threat, but the miss. Not the danger, but the knowledge. 3. Atlas taught us about the universe and our place within it, about vulnerability and capability, about cosmic processes and human resilience, about what's possible and what's probable, about the difference between imagination and reality. But most importantly, it taught us through its absence of threat, through its safe passage at comfortable distance, through being exactly what most cosmic visitors are, interesting, educational, scientifically valuable, and ultimately harmless to us. That's the gift we received, the knowledge without the danger, the perspective without the catastrophe, the awareness without the impact, the lesson without the loss. And as you drift off to sleep tonight, you can appreciate that gift fully, can rest knowing that we're safe, that we're watched over not by fate or luck alone, but by our own systematic vigilance and growing capability, that the night sky remains peaceful and will remain so for the foreseeable future, that tomorrow will come safely. The visitor from beyond came and went. We observed it, learned from it, and remained safe throughout. We're still here, still continuing our journey through time and space on this remarkable planet, still building, still learning, still preparing for a future we can influence. And that's exactly as it should be. That's the universe operating normally, with vast distances providing natural protection, with our vigilance watching carefully for exceptions, with our capability ready to respond if ever actually needed. Sleep well tonight, knowing that 3i Atlas passed us by safely, that tomorrow will come as it always does, that the cosmic visitor left us with wonder and knowledge rather than catastrophe and loss. That's the real story of 3i Atlas. Not a close call we barely survived through luck, but an opportunity we fully seized. An opportunity to learn, to prepare, to appreciate clearly what we have and what we're capable of protecting. And what we have is this: a safe planet orbiting a stable star, a watchful species with growing capabilities, and a universe that, while dynamic and occasionally dangerous, is mostly vast empty space that keeps us safe from harm through simple geometry and probability. 3i Atlas is now millions of kilometers away, continuing its ancient journey through the galaxy, and we're here, still orbiting our stable sun, still protected by vast distances and our own growing vigilance. If you've enjoyed this journey through the cosmos tonight, if these explorations help you understand our universe a little better, I'd be grateful if you'd subscribe to the Sleepy Astronomer. There are more cosmic questions to explore together, more mysteries to contemplate, more perspectives to gain as we drift through space and time on this remarkable planet. And if this particular question resonated with you, a like helps others discover these late-night wanderings through the universe. Thank you for joining me on this exploration, for imagining possibilities with me, for thinking through scenarios both sobering and ultimately reassuring, for staying curious about the cosmos while finding peace in our place within it. The sky above remains peaceful tonight. The stars shine as they always have. No comet threatens us. No interstellar visitor approaches on a dangerous path. Just the quiet continuation of our orbit through space, safe and stable. Tomorrow the sun will rise, as it has for billions of years. You'll wake to the same world, enriched perhaps by new perspective, but unchanged in its fundamental safety. This is the Sleepy Astronomer, wishing you clear skies, peaceful dreams, and the comfort of knowing that we're watched over by vast cosmic distances, by dedicated scientists, and by our own growing capability to protect this precious world we call home. Sleep well, safe under our sky,